Oh, hi. Hi. How's everyone doing? Let me check if the sound is all right. Hi, Vizzy. Glad to have you here. We'll wait until 7 and then we will begin. Hi, Elton. Welcome. Welcome to the stream. Hi, Inventive. Hi, uh, Schwellen. That's sorry, I can't pronounce the third guy's name. Good morning. 4:30 a.m. My goodness. Thank you for the dedication, man. Thank you. And by the way, Vizzy, well, you know that I have an alternative streaming schedule, 8 a.m. Unfortunately, I can't do that on most weekdays, 8 a.m. here. Well, you can convert that to your time zone. But I do try to set up a alternative stream, um, most most likely during the weekend. This way, people from a different time zone than mine have a good opportunity to join. But that's the best I can do. Yeah. So already 10 people. Wow, that's crazy. Inventive. I'm good. I'm doing great actually. It feels great to get the channel back for sure. Yeah. All right. So it's 7. So it's time to start the stream. All right. Just in case people who doesn't know what happened to the channel, we'll talk about this in Discord. All right, great. Yeah. Vizzy is right. We can talk about a lot of things in the Discord. You can find the Discord server in my about page or in the latest post. Or actually, not the latest post, the post yesterday. You can just go to the about page and find the Discord server. Now let's get into the problem. Yeah, I know. Like I'm trying to warm things up a little bit. Hope you don't mind. Unless you got like a deadline after the stream, so better hurry. I hope that's not the case. And actually, if that's the case, I will refuse to do the problems for you because I don't want to just do somebody else's homework, right? Vizzy, I trust you. Okay, so I don't do people's homework. All right, so sorry to disappoint if that's the case. But anyway, so yeah, I was just to let everybody know what happened to the channel. So now I have full control of the channel. Unfortunately, I lost access to my channel due to a phishing scam on Monday. You can actually you can go to my 2.0 channel. Okay, okay, great, Vizzy. No deadline means you got to walk the straight and narrow. Okay, to do mathematics. There's no shortcut. There's no pressure. There's no even a reason to create a shortcut, right? So that's the idea. I mean, yeah, on Monday I lost my channel due to a phishing scam. Some hacker pretend to be a manager from Grammarly and wanted a collaboration. So actually, they gave a legit Grammarly collab link. But then somehow they rewired it. I don't know why. But the thing is, like, it looks super sus. I mean, now it didn't look that sus when it happened to me. So the first thing they did is they asked for my channel URL, which I copy pasted, and then the next step is like a Google login interface. Okay, it looks exactly like a Google login interface. The graphics are the same, which it's just particularly scummy, right? And it asks for uh, your credentials and even the two-step verification, all of those things, right? So I did. and it's super sus, right? Because why would a potential sponsor would need my credential? I just it was completely. I mean, I was too naive, right? But here's the thing, right? As they say, fool me once, shame on you. Fool me twice, shame on me, right? So there's that. Basically, I lost access to my channel on Monday, and right after, like just within minutes, a live stream about some crypto scam, I suppose. I mean, I didn't even watch much of it. I just feel disgusted that somebody was running a live stream on my own channel. Yeah, so, and immediately after, YouTube took the channel down. It was deleted. It was completely obliterated. Okay, and there's that. So, unfortunately, so I was locked out of my main Gmail and my YouTube because the scammer changed everything on their end. They changed the recovery phone, the recovery emails. I lost money to scammers once. Sorry to hear that, Vizzy. Yeah, it sucks. Yeah, it sucks. I hope these people go to hell. Right? They have a special place in hell. Okay. Anyway, so yeah, where was I? I was talking about working with Google, right? Because I was locked out of my Gmail account and my YouTube account, so I have no way to automatically recover. I mean, by automatic, I mean without a human assistant. Right? I couldn't do it. The Google recovery page locked me in a loop. I couldn't proceed. So the amazing people on my Discord reminded me that I can actually create an X account and add Team YouTube on X, and they will take a look, right? So that was the only reason I'm able to recover my channel right now. Okay, that's the only reason because back then I didn't even have before the incident I didn't even have an X account or Twitter. I just never used it in my life. Okay, but I had to. I had to start a brand new X account, and to my great surprise, they replied on the same day. Okay, just God bless Team YouTube on X and Google support staff in general. I mean, I was like, well, they might not even have the appetite to respond. Like, what's the big deal? You know, it's not like I'm a I'm a internet celebrity or anything. I mean, I have slightly less than 20K subs. Big deal. I mean, on from a YouTube platform as a whole, right? This might look like a relatively big channel, but there's millions of channels like mine. So why would they even bother? Right? If they don't bother, that's that's kind of understandable as well, right? It's not like Google's have anything to lose right there. So yeah, I was very much surprised. Perhaps I'm just too cynical, but anyway, my standard tend to be pretty low. Anyway, so, but they responded rather promptly. So and the main thing they need was the channel URL, but I didn't even save the channel URL before. I didn't even know that. So I would just like log into my YouTube as normal. Why would I need a channel URL? But then Kat, yeah, Kat on Discord reminded me to look through my browser history. Right. So with the help of Kat and also Google Gemini, I was able to locate exactly the channel URL, not the handle, because the handle @mathwithming can be altered by the hacker. So I needed the unchangeable channel URL that started with a UC. So I managed to secure that in my browser history. Again, thank you very much, Kat, because I wouldn't know what to do. Anyway, so because without the URL, Google couldn't do anything either, right? So yeah, so I managed to get the channel URL, and everything kind of followed through then. Okay, so that took a few days to figure out, and after Google received the information and they managed to get a hold of my account activity, they confirmed that it was compromised, so everything fell in place. I received a special portal to reset the password and all of that. That was done. That was done on Friday. That was done. Maxter, thank you very much. Yeah, I mean, we're not talking about actual math there. We're just talking about like how I got my channel back. So yesterday I got my channel back. So on Friday I got my Gmail back, and I resecured everything. Thank goodness they didn't seem to send emails impersonating me to scam other people. So thank goodness for that. And but I still didn't have access to my YouTube channel on Friday because there was still the community guideline violation, and I had to appeal it. But Google already knows what's happened, so that went through rather smoothly. So yesterday early evening, I got access back to my channel. So that was kind of surprising as well, because I thought, because yesterday was Saturday, right? They said 2 to 3 business days. So yesterday was a weekend. I didn't expect they would respond to me on a weekend. So yeah, I got my channel back on last evening, and I posted the first post after I got the channel back. So yeah, just in case that people don't know, like the new folks, I mean not the new folks, but the followers of the old channel, I have a new channel called 2.0, okay, called Math with Ming 2.0. Exact same profile picture, exact same channel banner, bring math to life, all the good stuff. It's just the 2.0, and it has a few re-uploads. Mostly the stochastic calculus and mathematical statistics. I do plan to rework some of them. Because right now the standard has risen a little bit on the channel. And you know what? For the tech people, it's super easy for them. Yeah, I know, right? For me, it was the end of the world. For the tech people who have access, that's easy. But anyway, so I was thinking about reworking some of the old videos. Like right now, the channel has gained more followers, and I have become slightly more proficient with editing videos and stuff, and also just explaining math in general. So I figured it's probably better for me to rework some of the old videos, even those who got a lot of views, like the geometry of statistics, rotational invariance of Gaussian distribution, and all of that, because I figured perhaps I was assuming a bit much in those videos. I was I was just using like results that I thought, or just standard results from usual linear algebra, like the orthogonal transformation. I figured this is not a linear algebra video, so I just use those, right? Apparently, a lot of people got very intrigued by this perspective. Thank you very much. And to be honest, they are quite interesting in my opinion. And normally, stats textbook don't mention those. I figured it's probably better for me to make separate, like a prerequisite video for orthogonal transformations in linear algebra, and then apply it to the Gaussian distribution or the t-distribution, for example. And perhaps we should talk about the chi-square and f distribution to make a full series, and all of that. Because, mathematicians and professors in academia, they write second, third editions of the textbook all the time. Like, just look at some of the most popular textbooks. Like, some of them are in their 12th edition now, right? So I think I've got enough excuse, okay, to rework old videos. Even though the math is essentially the same, but I think the presentation, the improvements in the presentation as well as pedagogy, right, counts as new content. That's just my excuse. All right, I was talking about the 2.0 channel. I don't know, like the 2.0 channel is not something I want to give up, because it now represents something very special to me. It means a lot. It stands for the support I've got. It's been 10 years since I had a linear algebra and stats class. So it can be challenging to follow. Yeah, exactly, right? So perhaps I was assuming a lot in one of the earlier success videos on my channel. So it's definitely worth expanding because, yeah, yeah, thanks, Inventive. So where was I? I was talking about the 2.0 channel. I don't want to give up that channel, abandon that channel entirely, because it now means something very special to me. It means the support I have. I really like the geometry graphical views of stats you do. Thank you so much. Yeah, I always figured, like, why don't we just add more connections to like linear algebra, right? Because it really, linear algebra is like the workhorse of statistics, both like the computational stuff, like the matrices and stuff. Everybody knows that. I'm in year 11, so I have to Google everything as I go. Yeah, so I should probably make people's life easier by just talk a little bit more about the prerequisites in separate videos, right? So as for the 2.0 channel, I don't want to give them up. I don't want to give it up. So perhaps it will be for more niche content. It can be more, let's say, technical. If let's say I omit a technical measure theoretic proof, right, on the main channel, I'll use the 2.0 channel as like my own reference, so to say. I just don't this way I don't just point to a textbook. Okay, the proof is here. Right? It's still difficult, for example, for most people to have access to get paywall material. Let's not forget, textbooks are expensive, papers are expensive. If you don't have institutional access, those aren't easily available, right? So that's the first purpose of the 2.0 channel, is to create some sort of repository for more niche content, okay? And what else? And also, yeah, just more niche material in general, perhaps even non-math stuff, right? So, and I was doing a last time, actually it was yesterday. No, yesterday I did a live stream on the 2.0 channel about me studying a new subject, because I got questions all the time on how do you study math, okay? How do you read math books? Okay? How do you gain insights to a subject, right? So those sort of things are kind of everyday message in my DMs and email, right? I mean, I do appreciate those questions because people think I'm able to give them intelligent answers, which I very much appreciate. But the problem is, I always find myself unable to discuss beyond just surface talking points, like, you got to participate, you got to do the exercises. Everybody knows that, even though those things are true, right? It just doesn't very productive, right? I was asking those questions, exactly, right? So it's a common question. It's totally fair, because math is not something you can just pick up like immediately, right? So it takes a lot of effort and determination and patience and all of those things. And at the same time, it's difficult to communicate with people, right? I try to create this little corner of the internet for people to have a community, but it's not always easy to get answers, to get support. Like if you're self-studying, perhaps the most aggravating thing is not math itself, but rather the feeling of complete isolation. That's why I quoted Isolation, one of the Joy Division songs, in the channel, the stream, the stream post for the self-study, right? If you can just see the beauty, those things I could never describe. These pleasures are wayward distraction. This is my one lucky prize. I just figured that it fits so perfectly of the experience of self-studying. You try to appreciate the beauty in the math, but you're in complete isolation, right? And it doesn't have to be. I mean, it doesn't really have to be, even though math is a solitary endeavor. But there's still, people who have the same aspirations, and perhaps with different background, but the same motivation, right? So that's why we can build a community and help each other out. I was I was saying, okay, if I get all these questions all the time, right? Like how do you self-study? I might as well just show. I had a live stream on how to self-study a new subject, especially like proof-heavy subjects, because you know, proof-based subjects are typically harder to learn compared to, say, you just apply a bunch of formulas and then just drill, right? Proof-based courses are intrinsically harder to appreciate because to understand, because you really got to know what is really going on. You can't really black box everything, right? You can't just mechanically apply a formula and then go on with your day. If you don't understand the definition, you can't go really far, right? So that's why I started a live stream yesterday just to show exactly how self-studying math is like. I mean, I have some degree of math maturity, but I'm not proficient with most areas of math. Let's not fool around here. I mean, I have certain experience with certain sub branches of math. That is true, but most of the math I don't know very well. Right? For example, abstract algebra is a big weakness of mine. I mean, it's not my fault. It's simply because when I was in university, abstract algebra was not part of the credits. Right? I don't need abstract algebra to get my degree, and the credit courses for getting my degrees are already pretty tough, and my schedules are filled. Right? So, and back then I didn't even know if I'm ever going to need abstract algebra. And there's that. So for all these reasons, I didn't take a single abstract algebra course in my university or in grad school. The only algebra background I had was, well, 2 semesters worth of linear algebra, and those are like box standard linear algebra. Those aren't honor linear algebra. They have some proofs, okay? They have some proofs, but they're not like super intense. Like I would say they're even easier than Axler's linear algebra done right. I didn't even know there's such a book called Axler's linear algebra done right. Proofs are not as important as the idea behind the theorem. I think in a sense that's true. Like the intuition that drives the proof is perhaps more important. But proofs are important for communications, because sometimes if you think you got the idea, but you haven't written down the technical proof, there might still be something that is fuzzy in your intuition, right? So that's the thing, right? Proof writing is a check on intuition. So in a nutshell, proofs are a check on intuition. Einstein says something like, reason can get you from point A to point B, right? But imagination can get you anywhere, right? That's kind of the idea. The intuition can help you bridge connections between 2 seemingly independent math subjects, right? Proofs cannot do that. Proof can only verify certain ideas that are indeed true or not, right? So that's why mathematicians put such a high place on proof, but that doesn't mean proofs are the only legitimate activity in mathematics. Proofs are important for checking the intuition and for communicating ideas. Right, so that's the thing. Where was I? I was talking about channel 2.0. So I was just using the 2.0 channel as a platform to show how self-study mathematics is like. I was studying a completely new subject, or I mean not completely new. I've heard about abstract algebra before, right? How couldn't I not heard about abstract algebra if I have a math degree? I did, but it was at a very surface level. I know about, well, the legend of Galois, but I mean that's not working knowledge, right? That's it. Right? So I wanted to show what is it like for someone with a little bit of a math maturity, right, but not the actual knowledge to self-study mathematics. What is that like? Right? So that was the main motivation. There's still fuzziness. People often find counterexamples to prove things. Knowledge is a process or a process of proof and refutation. Exactly. Inventive. You're completely right. Because the proof standard nowadays is not the proof standard back in Euclid's time. Right? Even the standard of proof can evolve, but that's the best thing we can do. Right? We try to be as rigorous as possible, but sometimes there's still crack in the reasoning. I mean, we try our best, right? It's not like if something is quote unquote proved, then it cannot be disproved someday later. It can also happen. What matters is the attempt, right? Because if there is no proof, then what guardrail do we have about our intuition, right? So that's the thing. All right, I think did I miss a message? Some stat and probability questions are hard. How to train our mind for them, especially for quant? Thanks. It's a very good question. Indeed, that's a very good question. Well, I would say what I would say is, of course, there's no silver bullet, right? And indeed, some problems are indeed hard. What we can do is to first of all, have some sort of database of knowledge, right? And that can only be obtained by practice, right? For example, if you've done a sufficient numbers of probability and stats problems, you would know, okay, what are the most common recurring themes? Like, for example, conditioning, right? Conditioning in probability and stats is absolutely crucial. Because sometimes if you want to consider, let's say, an event, there are so many possibilities for that event to occur. So what do? We divide that into cases. That's exactly what conditioning is about. So that's a recurring theme. So you wanted to have a database of some of the most common formulas and techniques. Okay, don't mechanically memorize them, but rather drill them through examples so it becomes part of your active knowledge. So that's the first thing. Right? A good foundation always helps. But then sometimes the problem can be intrinsically hard. What do we do? So can we simplify the problem? Think about this. Can we simplify the problem? Let's say you may not be able to solve the exact problem right away, but can we, let's say, introduce some particular assumptions about the problem? Let's say if the problem only assumes you have an IID sample, it doesn't say what distribution it follows, and the problem is unsolvable to you at that point. So how about we assume it follows an IID normal distribution? Right? And that's exactly how probability and stats works in practice as well. Because even nowadays, most of the formulas, okay, in introductory level statistics were developed for normal distributions. General distributions are just generally more difficult to handle, right? So why don't we just look at a problem and we can't solve it, right? So we introduce additional assumptions that makes things more trackable, right? To retain all the assumptions in the problem, and then you solve a special case. So that's another way to proceed. And last but not least, if you still can't even solve the simplified problem, can we do some sort of simulation, right? So this brings the programming skill a little bit into the equation, right? So but nowadays with the generative AI, you can, I use AI quite often, but I don't trust AI, not by a long shot, but I do audit the response given by AI. Right? It's your choice to take it or leave it. Right? So that's the idea. AI can be a very powerful tool, but it does make mistakes all the time. Don't trust and verify. Right? That's the procedure. So if you have problem with, let's say, some coding problems, let's say you want to simulate a distribution, you can ask AI how to do that. Right? Just don't give AI the full problem and let it solve for you. That's not very helpful. Instead, work on just one particular part. Let's say I want to simulate this distribution. Is there any way I can do that, right? And AI can give you a pretty accurate answer in most circumstances as far as those questions is concerned. Right? What is simulation? A simulation is what is called Monte Carlo simulation. Monte Carlo simulation is like generating random numbers. So, for example, let's say the problem is to calculate the mean of a distribution, and you don't know how to solve the integral. Right? So what do? You use simulation to generate a random sample that follows the distribution in the question, and then you calculate the sample mean, right, as an approximation to the theoretical mean. It gives you a close enough answer, but not quite exact. Right? That's simulation. Right? But anyway, so these are all the skills that can be developed along the way. Right? So I guess that's stat guy 01. That's my answer. I don't claim to be exhaustive, but that's some of the approaches I would consider. All right, so enough chit chat. I was, oh gosh, it was a half an hour already. But the main point for today's topic, today's live stream, is to hang on. Let me exit that. All right, yeah, is to solve these problems given by Visi. Okay, so these are probability problems, and we will try to solve them as much as possible as our first attempt, because I just received those problems. I didn't have a chance to take a look at them at all before the stream, so this is like an honest attempt. All right, so anyway, so if I struggle, then I struggle. Okay, that's it. There's no sugarcoating on this channel. This is not a PR department of math. This is not about showing how smart I am. That's not the point. It's just to show the honest process of doing math. Of course, I do make polished videos to, help people save time. But sometimes there's situations I cannot optimize the process away, right? So that's the idea. All right, enough rambling. Let's take a look at the first question. Consider a region R. You can show off a little. Well, what's the point, right? By x greater than 0 less than 1 and y greater than 0 less than 1 in the xy plane. Okay, so that's a unit square, right? That's a unit square, and it's an open unit square. Does not include a boundary. We randomly select a point on R and refer to the selected point as A. Okay, let's draw a picture. Okay, there's already a picture. That's pretty cool, but it's kind of painful to scroll all the time, right? So let me fix that. Can we perhaps make a copy of that video, of that image, and just crop that? Okay, I want to crop that. Okay. Okay, and I want the picture here. I want a picture. We probably will end up drawing our own picture, but here's a nice picture that we can work with already. Perhaps crop a little bit more this way. Hang on. What's going on? Where's the question? Oh, did I delete that? Sorry. So I want this picture, and I want the question. Here. Sorry guys, I didn't really have time to do that. Hey Ming, sorry to hear about the hack. Hi Mason, thank you. It was only for your quant videos. Was confused when the channel wasn't there. Yeah, yeah. I should have been more careful, to be honest. But then this is how we learn, right? All right. Oh, okay. Did I? Okay, I did have the problem. I did have the problem. And now it's gone. Hang on. Did I? I'll keep one intact. Okay, and I just want to show everything on the screen that I need. Okay, I don't need everything. I need this part. Okay, I need this part. What's going on? Oh, right. Yeah, I need this part. I need this part. Where are we? So this is the unit square. And we have a random point. Random point. What do we mean by random? Yeah, we assume that A is uniformly distributed. We assume that A is uniformly distributed on R, so that makes things easier. We know that the x-coordinate of A is uniform 0, 1. And the y-coordinate of A is also uniform 0, 1. And x and y are independent. That's a uniformly random point on the square. Let AB be a perpendicular line from A to the y-axis, and AC be a perpendicular line from A to the x-axis as shown in the figure. ABAC, that's cool. We call the rectangle OCAB as the rectangle of A, sure, where O denotes the origin. And let S be a random variable representing the area of the rectangle of A. Answer the following questions. Okay, so that seems pretty clear. We're just drawing a random rectangle inside a unit square. Okay? And what do we need? We need to calculate the expectation value of S. All right. Okay, let's do that. Let's do one part at a time. So what would be an educated guess? Well, we can denote the x-coordinate. Let's write that. Denote. And put that into blue. So this way, it's easier to distinguish what's the steps and what's the questions. Okay, denote xy, big X, big Y, the coordinates of A. Okay, since A is uniformly randomly chosen in the unit square, the unit square, xy in R2, 0 less than x or y less than 1. Can a single point be uniformly distributed? Yeah, certainly. You can talk about a uniformly random point on in a region. Inventive? You can certainly talk about that. Okay, and just to clarify that notion, we can modular some technicality because we don't want to get into measure theory. So basically, if we let S be a region, okay, let S be a region in Rn. Doesn't have to be R2, can be in Rn. Sorry, is it? Yeah. All right, Rn. What does uniformly mean? Yeah. Uniformly means this. Let S be a region in our definition. Okay. Modulo some technicality. Let S be a region in Rn. I'll draw a picture soon. A point P, and let's use a different letter because P is already probability. Let's use a point X vector. How about that? Big X vector. A point X vector is said to be uniformly distributed over S if what? If for any subset, here I'm modulo technicality, actually it should be any measurable subset, but No measure theory here. Just say any subset. Sorry, measure theory folks. For any subset of S, say a subset, let's call it, give it a name, say perhaps U, subset U of S. The probability of big X in U in the set U is the ratio between the volume of U over the volume of S. Okay? Once again, I'm using the volume modulo technicality because this is really the so-called Lebesgue measure that generalizes the notion of length, area, and volumes in 3D. Hello, Ming. Oh, hi, Trip. So every point in the interval has the same order being picked. Yeah. So that's the one wriggle. That's the 1D uniform distribution here, right? We're dealing with general n dimension here. Right, so let me draw a picture. So this is our coordinate system. Okay, this is our coordinate system, say Rn. And here you have a region S. The idea is we want to describe randomly picking a point in S without any preference. Right? I don't have any preferred location. So how do we describe that? Well, if you pick a random point X, and now we consider a subset of S. Say this is U. This is U. The chance that the random point X is in U equals the volume of U divided by the volume of S. Right? I'm using the intuitive notion of volume here. Hopefully that's clear. And which is suffice for this problem. Okay, Vizzy, you're with me? This is what uniformly means. A uniform distribution means that if you pick any subset S over the universal set, the probability of a random point appearing in that set, is it being included in that set, equals the ratio of the volume of the subset and the volume of the total set, the universal set. Okay? Okay. It's always a good idea to clarify these notions. Okay, so that's the definition, modulo some technicality. All right, so that's the coordinate of A. That's the coordinate of A. Okay, so and if you pick an if you pick a random point in the unit square, it is intuitive that the x-coordinate of A and the y-coordinates of A are independent and uniformly distributed over the interval 0 to 1. Does that make sense? Let me claim that, but if you're interested in the proof, let's do it in the appendix. Okay. Since A is uniformly randomly chosen in the unit square, x and y are IID, means independent and identically distributed. It's a common acronym in probability and stat. Are IID uniform 0, 1. IID uniform 0, 1. Okay. If you wish to see a proof, we can do it at the end. Okay. So that's the coordinates of x and y. The coordinates of A. The coordinates x and y of A. So by the construction of the rectangle, what's it called? OCAB. OCAB, its area S equals x times y. Right? S is the product of x and y. Okay, so the first question is immediate. We wish to calculate the expectation value of S, or the expected value of S. You know, physicists like to talk about expectation value, whereas statisticians typically say expected value or expectation, but not expectation value. Anyway, so here, potato, doesn't really matter. ES is EXY, E of X and Y, E of X times Y. And now we're going to use a property of independent random variables. X and Y are independent, so you can factor the expectation and write it as E of X times E of Y. E of Y, okay? And now we're going to use a property of the uniform distribution. It is intuitive that the uniform distribution has a mean of just the midpoint. Right? If the distribution is uniform over 0 to 1, the average for that should be 1/2. So you get 1/2 times 1/2, which is 1/4. So that's the average area. It kind of makes sense, right? It kind of makes sense because on average, the x coordinate of A is 1/2. So on average, the x coordinate of A lands in the middle, and similarly, the average coordinates of y, and the average coordinate y of A also lands in the middle. So on average, A lands in the center of the square. And of course, when A lands in the center, S is 1/4. Pretty intuitive. Okay? 2. Calculate the probability that S less than or equal to R. So this is a special quantity. The probability that S is less than or equal to R. This is called the cumulative distribution function of S. Okay? This is called the CDF of S. This quantity, treated as a function of a variable R, is called the CDF of S. And we usually write it as big F with a subscript S of little r. Okay, this is called the CDF of S. Well, technically speaking, in a CDF, the variable should take values over the whole real line. So R can be greater than minus infinity and less than infinity. Here we're only interested in R being between 0 and 1. The reason for that is S is an area. We know that S cannot be negative. So S has a 0 probability of being negative, so we don't need to calculate that. Also, S cannot be greater than 1 because the rectangle is a subset of the unit square, and the unit square has an area of 1. So S has 0 probability of being greater than 1. So what's interesting is the case when R is between 0 and 1. So that's the only non-trivial portion of the CDF. Okay, so let's calculate that. So we need the probability of S less than or equal to R for R greater than 0, less than 1. So how do we approach this problem? First, we can express S in the same manner, which is X times Y. Okay. And now we have few options to solve this problem. What do I mean? Well, X times Y less than or equal to R is also a region on the XY plane. Right? X times Y less than or equal to R is also a region. Let's draw that on the original diagram. We know the boundary X times Y equals R is a hyperbola. That's middle school algebra. So this is the curve of X times Y equals R. right? Wiener. What do you mean? So yeah, this is a boundary of x times y equals r. And what we want x times y less than or equal to r. So what region is that? Well, it's below this hyperbola. It's the region below this graph. But also, x and y has to be in the unit square. So we're talking about the region that's inside the unit square and is below the hyperbola. Right? We want that. So that's the region. So that's what do we do with that? What do we do with that? Well, we can think of this problem as finding the probability of x and y simultaneously satisfy two conditions. First, it needs to be in a unit square, and second, it needs to be under the hyperbola. So what we need to do is to integrate the joint density of x and y over that region. And of course, the joint density in this case is a constant because it's uniform distribution. If a distribution is uniform, its density, the joint density is constant. That's a basic fact. So that's our first idea, is to simply integrate over this shaded region. You just integrate the density over the shaded region. That will be it. That's the probability. And of course, this region is a little bit irregular, right? This region is not super nice. So what do? We calculate the integral over the complementary region that is above the hyperbola. So what this means is, I'll draw a separate picture. Okay, I'll draw a separate picture. Okay, method 1, use joint density. Method 1, integrate the joint density. Okay, I should probably write down the general formula here. Going back, right, this is like a review section. Uniform distribution. And now we're talking about formula. Consider random variables, RVs, x and y, that are jointly distributed. X and y with continuous random variables. With joint density S. Joint density, we usually write little f, and with a subscript of x and y, big X, big Y, and with arguments of little x and little y. Now, statisticians and probabilists typically denote random variables with capital letters, and their realizations, or the values of random variables, as lowercase, corresponding lowercase letters. This is a tradition. Okay, so then for any subset, once again, modulo technicality, any measurable subset. I'm not going to mention that every time. For any subset S of the support of fxy. By the way, what is a support? Support just means the region on which the joint density is non-zero. The support of fxy. It just means the support. This is a set x and y such that the joint density is non-zero. Okay, so we're considering a subset of that set of the support. Then for any subset S, the probability of the point x and y belongs to the set S is the integral over over the region S of the joint density. Okay, so it's a double integral. Even though I'm only using a single integral sign, it means a double integral. Actually, you know what? Let's write a double integral sign. The double integral over S of the density dx dy. Or you can write dA as the area element. So that's the formula. Okay? So we're using this method. Okay? So now we're considering the subset x times y less than r. So that's our region. Let me copy that picture here. Change the format to be this way. Okay. I want this way. Where did the picture go? God damn. What the hell? All right. So let me just draw it here. So that's the region. X times y equals r. And let me shade that. So we're integrating the density over this region. But of course, this region, this L-shaped region, is a little bit cumbersome to integrate. So we can integrate over the complementary region and use 1 minus. Okay. By that I mean the probability of x and y less than or equal to r is 1 minus the probability of x times y greater than r. And also x and y is in the unit square. Okay. So we're integrating over this region here. We're integrating over this region. So we're calculating a double integral. So to calculate double integral, there are many ways to do that. We can choose an order of integration. If we integrate with respect to y first while fixing x, visually that means drawing a vertical line this way. So we temporarily fix x. Then what would be the range of y? Well, on this line, y is less than 1, which is always true, and is greater than r over x. Right? Because x times y on the red region is greater than r, which is equivalent of saying y greater than r over x. So that's the range of y when we fix x. So let's calculate that. The probability using the formula that I just wrote, this is an integral. Hang on, what's going on? Dang it. This is a typesetting nightmare, huh? This is disgusting. I don't know why. But here, okay, so let me... okay. Something is messed up here. Something is really messed up in MS Word. But can I maybe group this thing? Group them together? I should have put them in a box. Perhaps it's not too late to do that. Okay, it's just stupid. Me forgot how to typeset everything properly. Oh, it's now stuck. Huh? It's now the MS Word just officially crashed. Okay. Anyway, all right. Let me try again. Did I have the picture? I cannot type things properly. Maybe I should just use OneNote next time. Edit anyway. First of all, you know what? We'll save that later. We'll save that later. Okay. So this is the 1 minus the integral, the the integral over the region. The region is x and y greater than 0, less than 1. Oh no, yeah, it should be fine now. It should be fine now. And x times y greater than r. So we want to integrate over this region. And the joint density, here, little f is just 1. It's just 1 because the total area is 1. The total probability is 1. The density is the total probability divided by the total area for uniform distribution. So 1 divided by 1, so the density is 1. So just dx and dy. Okay? So to calculate that, let's do 1 minus. As we said, we can convert this double integral. I didn't know you can type LaTeX. It's not technically LaTeX, it's just the equation editor, which I figured for live stream is better is better than LaTeXing, because LaTeXing is not super intuitive, right? What you type is not what you get. And I don't want to have like a huge chunk of block of LaTeX code on one side and the rendered version on the other side. It just gets super overwhelming. I just use MS Word, okay? It's kind of inefficient, but it works. All right, so we need to figure out the region of integration, right? So here we're only integrating over the red region, the complementary region. As we said, if we fix x, then y is greater than r over x and is less than 1. You could, yeah, I could, so I believe the built-in, yeah, it's the built-in equation editor. So the problem is, how do we decide? Can I move this? Yes, thank you very much. What's the extent that this vertical line can move? Well, x is less than 1, that's for sure. But what is the leftmost position? Well, at the leftmost position, we're talking about the boundary point on the hyperbola in which y is 1. Right? So here you have x times y equals r, and when y is 1, x is r. Let me put that down. So that coordinate is r. So the point here, this point here is r1. It satisfies x times y equals r. So the integration region is set to be from r to 1. That's the bound for x. That's the bound for x. And then when x is fixed, the region, or the range for y, is from r over x to 1. So r over x to 1. This way. And then we integrate dy first, and then dx. And then dx. So that's the double integral. And the integration itself shouldn't be too hard. Let's just integrate everything one at a time. Let's, just to make this super obvious, we're integrating the inner integral and then do the second. Right? It's like from inside to the outside. So 1 minus the integral from r to 1. And you got, here we're just integrating a constant, right? Because the function is not dependent on y, so it's simple. So it's just 1 over r over x this way. All right. All right, so that's cool. And then what else? We need to integrate the outside integral, dx. And this gives us 1 minus, use the fundamental theorem of calculus, x minus r times the natural log of x. And the bound is from r to 1. So evaluate at both ends, 1 minus. Let x equals 1, you get 1 minus r times the natural log of 1, which is just 0. So we evaluate the function when x equals r, so you get r and then plus r times the natural log of r. All right. Okay, so that's the calculus done. And then you simplify, you get r times 1 minus the natural log of r. Let's think about whether this makes sense. First, this is a probability, so it must be between 0 and 1. Is that the case? Is this thing between 0 and 1? Well, r is certainly less than 1. But what happened here? Is this thing less than 1? Well, when r is less than 1, natural log of r is negative and can be very negative. It can approach minus infinity. So 1 minus the natural log of r can actually approach minus infinity. Sorry, it can actually approach positive infinity. So 1 minus the natural log of r can approach positive infinity, which means we don't know for sure whether the product of r times the natural log, 1 minus natural log of r, is between 0 and 1. We don't know. We don't know. So it's worth investigating the property of this function. How does this function behave? Just as a check. I am extremely aggravated by this painful picture. Let's just, you know what, delete everything because I cannot stand this anymore, and redraw it with my bare hand in the drawing region, because this is absolutely aggravating. My goodness. All right, so let's redraw using our bare hand, which is not that hard. I shouldn't be lazy and use the default picture. There you go. There's a nice coordinate. There's a nice unit square. Here's a curve, the hyperbola, x times y equals r, and we're integrating over the complementary region. Okay? And to do the double integral, let's fix x. That's not the only approach, by the way. You can fix y too. When you fix x, y is greater than r over x and is less than 1. And here, the boundary point has x coordinate of r. Okay. So this is a corresponding picture for the double integral. So just as a check, let's figure out what's the behavior of the function. Check that r times 1 minus the natural log of r. This needs to be is in 0 to 1, because that's a probability. And also there's something else. The cumulative distribution function, the CDF, is always increasing. That's just a general property of the CDF. So meaning when r gets larger, this probability gets larger and increasing. Which is just a simple problem in calculus. Let's denote this function as FSR. Okay, FSR. That's the standard notation for CDF. So let's calculate the derivative just to make sure everything is okay. Calculate the derivative will give you information about whether, well, there are many isoquants between isoquant. You mean this curve right here is isoquant? I wouldn't use that term, but anyway, I get what you mean, right? The contour of the function x, y equals r. I want to check this function is in 0 and 1 is increasing. So let's first check the increasing part. Take the derivative, gives you 1 minus the natural log of r. And then plus, use the product rule in calculus. R times what? R times the derivative of 1 minus the natural log of r, which is the derivative of that, which is 1 minus 1 over r. So r times minus 1 over r. So negative 1 gets cancelled, so it's just negative natural log of r, which is positive. That's nice. It's indeed increasing. It's indeed increasing, so let's check the boundary behavior. What happened when f approaches, let's talk about the limit when r approaches 1 minus, okay, that's the left limit. R is anything between 0 and 1. Yes, R is between 0 and 1. I want to check whether the CDF is between 0 and 1. Right? That's a probability. It's supposed to be a probability. Right? So it's a nice way to check. Okay, so when R approaches 1, well, the natural log of R approaches 0, so it's just 1 times 1. Right? So it's just 1. That's easy. But when R approaches 0 plus, you got to use the L'Hopital's rule. Yeah, it's not inclusive. Yeah, R is strictly less than 1. I'm talking about this value here. Is not included. I mean, if it is strictly less than 1 and strictly greater than 0, it is still in a closed interval, right? By the virtue of being a probability, it is greater or equal to 0 or less than or equal 1. Right? So this is still a valid statement. Right? Just let me add that, okay? Since it's supposed to be a probability. Okay, so that's what I'm trying to verify here. And then you got the limit of r goes to 0 plus FSR. This way, here you need to use the L'Hopital's rule because that's a 0 times infinity situation. You got a 0 here and an infinity here. You cannot just directly plug in and get the limit, unlike the 1 case. Okay, so what do we do? Instead, we rewrite the expression as a fraction so that the L'Hopital's rule can be applied. You get 1 over r at the bottom and 1 minus the natural log of r on top. So now this is an infinity over infinity, which we can use L'Hopital's rule. Just standard Calc 1. It has nothing to do with probability anymore, just standard Calc 1, which reminds us of the importance of foundation. Okay, so at the bottom you get negative 1 over r squared. On top we have a minus 1 over r. Okay, so simplifying just gives us r, and r tends to 0, so the limit is 0. So that's cool. Okay, so you just get r, and taking the limit gives us 0. Okay, so let me draw the picture here. What we've just managed to verify is the following. Here, the graph of the function, probability of s less than or equal r is strictly increasing over interval 0 to 1. And its graph looks like this. Okay, I mean, I draw a concave function, but a convex function, and it's actually true because if you take the second derivative, actually the second derivative is negative. It should go like this. It should be a concave function, not convex, because the second derivative is minus 1 over r. It's negative. Right. But anyway, that's the idea. All right, so we managed to get this result, the joint density. Okay, that's the joint density. And the method 2, which is also very common, is to use conditioning. This is the method 1, integrate the joint density. Method 2 would be conditioning. This is also a very common method for a multivariable probability problem, just to use conditioning. What do we mean by that? Well, we can control one variable to be fixed. That's the idea. So we're interested in the probability of x times y less than or equal r, right? Yeah. Um, so the idea is we keep one of the variable fixed. Let's write that down. Okay. Next formula is called the law of total probability, or some variant of it, because the law of total probability really has different versions. The law of total probability. The laws of total probability. Okay, so let's start from the most basic version. The laws of total probability underlies all the methods for using conditioning. All right. So first, let's do the version for simply events, which is rather straightforward. So consider let A and B, A1, okay, A1 and A2, so to say, A1, A2, and B events. Suppose A1 and A2 are mutually exclusive. Which means they're disjoint and their union is the whole sample space. Are mutually exclusive or disjoint, okay? Mutually exclusive. And A1 union A2 is the big set, which we usually denote as omega in probability theory. All right, so then what we have, I'll just derive it on the spot, PB. What's PB? PB is the probability, we can write it as A1 intersect. When we say intersect with another set, we simply don't write the intersection symbol. Okay, that's a common notation in probability. A1B, which means A1 and B. Union. You still need to write union. A to B. Okay, what does this mean? What does this mean? Let's insert a drawing space to illustrate that. So suppose you have the sample space like so. This is all the outcomes, omega. And we can divide the big omega into two sets, two events, A1 and A2. For example, omega is the total population. A1 is the people who smokes. A2 is the people who doesn't smoke. Okay, and the event B is the set of people who unfortunately have lung cancer. This is B. Okay, so let's say we are interested in calculate PB. What do? We add up the two portions. Okay, one portion is A1 and B. This is A1 and B. They're obviously disjoint, so we can just add their probabilities together. Equals A1B plus PA2B. Okay, and what is that? Well, we can express the two in terms of conditional probabilities. Okay, the first joint probability is the probability of B given that A1, and then times A1. That makes sense? So the first probability here, the conditional probability, refers to the probability of having, say, lung cancer, provided the person doesn't smoke. So you're given the prior information that the person doesn't smoke, but still unfortunately has lung cancer. Right? And you weigh that probability by the probability of A1 itself. Right? So imagine, how do you calculate the proportion of a population that does not smoke but still have lung cancer? Well, you calculate, first you look at how many people, what percentage of people doesn't smoke, and then you multiply that by the percentage of people who has lung cancer in that group, the multiplication principle. Okay, and then you add the second probability, which is PB given A1, A2, and then times PA2. So that's it. That's the law of total probability for two events. That's the total probability for two events. The idea is hopefully these two conditional probabilities are easier to calculate than the joint probability. That's for events. Law of total probability for events. LTP for events. So that's the first version. And we can generalize that. In general, let you have A1, A2, okay, be all the way to AN, NB, be events. Suppose A1 all the way to AN are mutually exclusive, and the union is the big omega. So instead of having just two groups for the whole population, you have n groups are mutually exclusive, and their whole union is big omega. Then by exactly the same principle, we can write it this way. So I'm going to rewrite it shortly, very quickly. The sum, the PB is the sum of PAIB. All right, is the sum of PAIB. Let me draw the picture on the side, just to illustrate the n cases situation. So here you have the sample space once again. A1, A2, all the way to AN. So all these events partitions omega. And then you have a B, general event B here, which may or may not overlap with every one of them, but that's okay. If B does not say overlap with A1, A1 and B is simply the empty set, okay, which has probability of 0. Okay, and then we express the joint probability as such. B given AI times PAI, and that's it. Multiplication principle for each term. Right, LTP for event. Okay, cool. What am I trying to get to? We're trying to get to LTP for random variables. Okay, LTP for random variables. Here I'm just going to write it for here I'm just trying to write it for continuous random variables. Okay, suppose we have X and Y are continuous random variables. Okay. Continuous random variable. So let's try to calculate an event that involves the two random variables. Okay, let S be a subset of the support of f x y, the support of the density. Then what's the probability of x and y belongs to that set S? Well, the idea is we can control one of the variables to be fixed, and then calculate and then use the conditional density. Okay, so this becomes the integral of the conditional density. Say I'm fixing y temporarily. So this refers to the joint density, sorry, not joint, but conditional density of x. Suppose that y is fixed. And then multiply that, weigh that by the density of y. dy. Yeah, that makes sense. Actually, that actually not quite. So this should be, no, this is not correct. This should be the probability of, this should be the probability of x and y in S, given that y equals little y. Yeah, that's more like it. Yeah. So the idea is we're controlling the second variable. Suppose that big Y is little y. And then we calculate this probability, the desired probability. Suppose that y is fixed. And then we're going to take the weighted average, so to say, of this probability. But instead of a sum, we have an integral. This is also a very common strategy for joint distribution, because here it's easy to draw a 2D region, right? But what if you have multiple random variables involved? Then it becomes hard to draw 3D or even 4D region. So that's another common strategy for handling joint events. Use conditioning. Okay. So we're an hour and a half into the stream, and we still got 16 people, so that's amazing. I don't know why would somebody watch somebody else do math while there's like gaming content on YouTube. Okay, thank you guys so much. Yeah, but that's the two main strategies here, right? So this is a method one we just calculated, right? And next we're going to use the law of total probability, aka conditioning. Two very common approaches. Let's do that. Conditioning, method two, conditioning. So I'm trying to create a conditioning formula here. So let's think about what would be the region of integration. So let's actually first, I'm just going to put two dummy symbols here. It doesn't mean it has to be 0 to 1. Okay, I'm just put the blank space here. I want to integrate x times y less than or equal to r by my own formula, such that big Y is equals little y, and then times the density of y dy. All right. Okay. So how can we can we now set up the bound of integration? Well, if we don't know any better, we can always write the default range for y, which is from 0 to 1. Yeah, that's okay. And what about individual terms? Right. So this is the conditioning formula. We need the individual factors. The joint, no, not the joint. The marginal density of y is very easy. Biostatistician here watching. Thank you very much. Yeah. Yeah, and don't hesitate to point out mistakes here, Peter. So here, y, as we said, is uniform 0, 1. The joint density, not the joint density, but the marginal density is simply 1. Y goes from 0 to 1. That's something we can easily find out. Okay, but what about in the middle? When big Y equals little y. Okay, we're treating y as fixed now. We're treating y as fixed. What's the probability of x times y less than r? Remember, x is less than 1. So if y is less than r, x times y is automatically less than r, right? So recall, both x and y less than greater than 0, less than 1 with probability 1. right? Both of them less than 1. So we consider two cases. We consider two cases for the conditional probability p x times y less than r such that y equals little y. Case 1, y is less than r. If y is already less than r, since x is less than 1, then x times y is automatically less than 1. In this case, this conditional probability is simply 1. Okay, nice. Case 2, when y is greater or equal to r, but still less than 1. Okay, so y, let's write it this way, y is r less than or equal to r, r less than or equal to y less than 1. In this case, what happened? Well, we treat y as a constant. So now, if we don't control x at all, it is possible for x times y to be greater than r. So for that, we need x to be less than r over y. Right, so that this can happen. In this case, the probability, the same conditional probability, can be expressed as following. First, we do a substitution. Whatever is conditioned on can be substituted into the event that is to the left of the vertical bar. Okay, that's the substitution principle. It's x times little y less than r such that big Y is equals y. Okay, so that's the substitution because y is given. And now just by algebra, x is less than r over y such that y is equals little y. Hang on. So yeah, that's just simple algebra. But then x and y are independent. And the event here, x less than r over y, because there's little y here. Little y is simply a number. Okay, so that's not a random variable, which means the two events, x less than r over y, and the second event, y equals little y, are independent. So you can simply drop the condition. Okay, so now you can drop the condition because of x and y are independent. Let me put that down here. Okay, so you can drop that. And now it's just a marginal probability of x. A marginal probability of x, since x is uniform. Right, since x is uniform, this is just 1 minus r over y. Use the uniform distribution formula. Okay, that's the second case. And now we're integrating over from 0 to 1. And we have two cases for this formula, therefore we need to break the integration in half. So therefore, this integral, let's call it star. The integral star has two terms. The integral star equals the integral the first case from 0 to r. The conditional probability is 1 times the density, which is also 1, then dr. That's the first piece. And the second piece is from r to 1. And then you integrate 1 minus r over y dy. And then evaluate both to get the answer. So the first term is r. The first term is simply r. The second term is, okay, you got y minus r times the natural log of y. Don't need the absolute value because y is positive. from r to 1. Evaluate both ends, you get when y is 1, you get 1 minus 0, so no need to write that. So minus r actually plus, no, plus r over, let me do that slowly, okay? 1 minus bracket r minus r natural log of r. Something is wrong here, no? Something is wrong here. You get 1 plus r times the natural log of r. What the hell? It's not the same as what we have earlier, huh? Hold on a minute. Do we get this? When y is less than r, the probability is, conditional probability is 1. So integrating from 0 to r dy is just r. Second case, from r to 1. Oh, actually, this is stupid. This is just r over y. This is just r, because x is uniform. Remember, x is uniform 0, 1. 0, 1. R over y is here. So the probability of less than r over y is simply r over y. There's no 1 minus here. Okay. Okay, that's where I got wrong. Okay, so no 1 minus here. Then it's simply the natural log. Right? And it's simply the natural log of r times the natural log of y. Okay, when r equals 1, so when y equals 1, this term cancels. Yeah, so terms cancel, so it's just 0 minus r natural log of r, and this simplifies to the same answer before. Hooray! We got the same answer. Okay, so this is conditioning. How about that? Okay, this is method 2 conditioning. We use the law of total probability. And as an additional check, because we calculate the area, the mean of the area. We calculate the mean of the area. There's actually a way to verify this. Well, you can use the CDF to directly verify that, or you can calculate density and then verify that as well. So let's use the density. Additional check against what? To see, basically, additional check whether if yes is 1. Oh, sorry, not 1, but a quarter. Okay. Okay, let's check that. Well, fs of little r is r 1 minus the natural log of r between 0 and 1. Okay, so that's the CDF, and the density, little f, is big F, the big F taking derivative, which we just calculated here. We verified that is the minus natural log of r. So that's the density. It looks rather weird because there's a minus sign, but remember, r is between 0 and 1, so this is actually positive, so we're good. Okay, so that's the density. And ES, by definition, should be the integral from 0 to 1 Fs r dr. I put r up front. Okay. So this is a definition of expected value for continuous random variables. Let's plug in the density. So it's minus r, the natural log of r. Let's do the natural log of r first. Okay, and then times r dr. Okay, so now we're left with this integral to calculate. So back to Calc 1. How do we evaluate this integral? We use integration by part. So this is something that should be rather standard. When you see a transcendental function multiplied by a polynomial in the integrand, use integration by part. So what we do is we treat r dr as a whole, that is d of half r squared. Let's write that. So this is the integral from 0 to 1. We're going to use IBP, okay, integration by parts. You get minus the natural log of r, and then d of half r squared. All right. So using integration by part formula, it should be minus the natural log of r times half r squared. Half r squared, and then we impose boundaries from 0 to 1 minus the integral from 0 to 1 d of natural log of r, d minus the d minus natural log of r. This is the integration by part. Okay. Okay, so what happened here? When r equals 1, this is obviously 0, because natural log is 0. When r equals 0, you got to use the L'Hopital's rule argument again. Okay, let's put that in detail. Okay, so we need the limit of r approaches 0 plus, okay, of minus natural log of r times half r squared. No, so that's the 0 endpoint. When you plug in 1, it's always 0. And it should be 0, but let's verify that carefully. So let's pull out minus half r up front. Okay, r goes to 0 plus, and you got natural log of r on top, and let's write times r squared as divided by r to the minus 2. So let's use L'Hopital, because this is infinity over infinity. Just nothing to do with probability anymore. It's just pure calculus. Okay, minus 2, minus 1/2. This is the limit when r tends to 0 plus minus 2 r to the minus 3, minus 2 times, and on top you got r to the minus 1. So everything simplifies to 1/4 the limit when r approaches 0 plus, and you get r squared here, which is 0. Okay, the limit of r squared is 0. So the first term completely cancels, and we just left to integrate the second term. Okay, so let's put the 0 here. So this is 0, see below. All right. And then we calculate the integral. Now the integral should be easy. Minus and minus cancel. 1/2 get pulled to the front. Integral from 0 to 1, r squared. D natural log of r is 1 over r dr. dr. All right, so this is 1/2 the integral from 0 to 1 r dr, and that's 1/4, exactly as we calculated in part A. So this is correct. So this further confirms that our answer to part B should be correct. 1/4 here, 1/4 here. All right, that's cool. Calculate the density. Well, the density we just calculated. Density is easy. Just differentiate big F is just minus R. Okay, so I'll just wrap that up real quick. Part 3. The density, little f of S. This is big S, big F prime. Big F prime. That's minus natural log of R. R is between 0 and 1. This is something super important, because whenever we give our answer for a density, we always write the support. Otherwise, it's unclear what the support is. Okay, or otherwise, I mean, it's not immediately clear what the support is. Always write the support to accompany the density. That's something we always do. Okay. So that's the 3 parts here done. Okay. Anyway, let's keep going. Is there anything else? Again, consider region. Okay, so there's a part 4 here. There's a part 4. Let me do that. This is a part 4. Same region. Again, consider region R. Let n be a positive integer. We select n points on R and refer to the points as a1, a2, all the way to an. We assume that each of the points is uniformly distributed on R. Okay, and ai and aj for I not equal to j are selected independently. Answer the following questions. Okay, so you have a bunch of points. So by the same reasoning, let's denote the coordinates of ai as xi, yi. Okay, denote, put that to blue. Okay, denote xi, yi, the coordinates of ai. AI for I equals 1, 2, and 3. And 2, 3, 1, 2, 1, 2, and all the way to n. Okay. So we have, since AIs are, since AIs are independently drawn, independently and randomly drawn from the unit square. We have x1 all the way to xn and y1 all the way to yn id uniform 0, 1. All right, so that's what we can conclude from this construction. Let Si be the random variable representing the area of the rectangle AI. So now we're constructing the rectangle for AI in the same way as in part 1 to 3. Let Z be the random variable, which is the minimum. Calculate the probability density function. So, okay. Well, by part 2, the areas, for each I equals 1, 2, all the way to n, the area Si of the rectangle of AI follows the distribution given by the CDF FSR equals R times the natural log, 1 minus the natural log of R, where R is between 0 and 1. Okay, so and since SI is right, SI is xi times yi times yi, and since and by independence of AIs, okay, and by independence of AIs we have S1, S2, blah 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 to Sn IID. These are IID, and each has the distribution FSR. Okay, so this is what we can conclude from this construction, and also Z. Okay, since Z is the minimum of S1 all the way to Sn, we want to calculate the density. Well, for this kind of question, we should perhaps consider the CDF of Z first, because that's a probability. The rules for manipulating probabilities are way more than the rules for manipulating densities. So whenever possible, we try to consider probability first because they're easier to think about. So if we try to, let's say, consider the CDF of Z, that would be the probability of big Z less than or equal to little z. Right? Let's think about that. So I'm here at a drawing region, just as brainstorm. Okay, so how do we approach this? Let's say if I want the CDF, let's consider the probability of Z less than or equal to little z, where little z is a constant. What would that mean? It would mean the probability of the minimum of S1, S2, all the way to Sn, less than or equal to little z. But the problem with this is there are so many cases, right? So imagine you have the values of S1 all the way to Sn. They're between 0 and 1. We know that for sure. Right? So these are the, let's say, these are the values of S1 all the way to Sn, scattered here. We don't know their order. We don't know anything in detail about them. So we're just saying, okay, the minimum of these numbers should be less than or equal to z. Okay, we want that event. And we don't know how the second minimum, okay, the second minimum behaves. We don't know the third, how the third minimum, the third smallest, okay, the second smallest, third smallest element. We don't know how they behave. So there's so many cases. And when that's the case, okay, when the event becomes too complicated to analyze, let's consider the complement. Let's consider z greater than little z. Because if you know this, you immediately know the probability of z less than or equal to little z. They're a complement of each other. And now what we're looking at. We're looking at the probability of the minimum S1, S2, all the way to Sn greater than z. And that's relatively easy because the minimum being greater than z simply means all of them are greater than z. And SIs are independent, so this is just the product of probability of SI greater than z. And each of them is identically distributed, so this is just the product of 1 minus FSZ. So we're done. And then, so this way you get the complementary probability 1 minus that, take the derivative, boom, problem solved. Yeah, because you want the density of z. All right, so we can get rid of this now. Okay. We can calculate, since the z is defined as a minimum. This is, by the way, order statistics. This is a very special case of order statistics. Order statistics has a very rich history. Not very rich history, but very rich theory about them, and they're used in, say, for example, non-parametric statistics. But we will just mention that in passing. For any z greater than 0, less than 1, the probability of big Z greater than little z is, as we argued, the probability of, for all I, Si greater than z. And by independence, this is the product. This is the product of I from 1 to n, P Si greater than z. Okay, P Si greater than z, this is the product of 1 minus the CDF of Si. 1 minus the CDF of S, of S, yes, exactly. Okay, and because these are identical factors, you just end up with 1 minus the CDF of S raised to the n. Okay, so there's that. We now have the tail probability. We now have the tail probability, therefore, the CDF, the probability of z less than or equal to little z, is 1 minus the tail probability. And what we want the density. We want the density, therefore, little f of z is d over dz of the CDF. Okay, and what's the derivative of that? Well, 1 cancels. You got an n up front, use the power rule, times 1 minus FSR, quantity raised to the power of n minus 1. Use the chain rule times the derivative of the inside, which is the minus of little f SR. The minus sign cancels. Okay, now just plug in the formulas. You get n times, what's that? 1 minus r? Oh, no. 1 minus r, yeah, times the 1 minus the natural log of r. This is FSR. Yeah, this is FSR. R times 1 minus natural log of r. Right. Raised to the n minus 1. And then times the minus of natural log of r. Minus the natural log of r. So that's the distribution function, not the distribution density function of the minimum area. And once again, do not forget to write down the support. R is between 0 and 1. Okay? So that's the end. So that's part 4 done. Okay, I believe that's the end of this question. All right. Okay, so we're done with this part. Let's look at the next question, which is brand new. A coin with the probability of coming up heads equals to P. Okay, so you have a coin with P head equals P and is tossed n times. Let AM be the probability that the coin never comes up head twice in a row. What's n? Why is n here? Let A, this is it's tossed n times, that's why. It's tossed n times. Let an be the probability that the coin never comes up twice, come up heads twice in a row. And let Bn be the probability that the coin never comes up head 3 times in a row. Okay. Let A1 equals 1 and let B1 equals B2 equals 1. Because these are degenerate situations, right? Because if you just toss the coin one time, it's impossible. It's impossible. Why is it 1 but not why is it 1 but not 0, huh? An is the probability that the coin never comes up head twice in a row. For some reason, we're defining A1 to be 1. Oh, never comes up head twice in a row. Yeah. If you just toss one time, it's never possible to have head twice in a row. So A1 equals 1 makes sense. And similarly, we define B1 equals B2 equals 1. Okay. Obtain A2 as a function of P. Obtain A2 as a function of P. Okay, so let's think about that. Oh, there are so many parts. I guess the idea is to establish a recurrence relation. I guess the idea is to establish a recurrence relation and then use this theory of difference equations to figure out the general pattern. Let's think about A2. When you've thrown once, you never have gone, yeah, exactly. Yeah, Wriggle, you're right. Yeah, because An is the probability that the coin never comes up head twice in a row. Never. So, oops. So here we're dealing with A2. A2, we only toss 2 times, and we don't have heads 2 times in a row, right? A2. When you toss the coin 2 times, there are 4 possibilities: head, 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 tail, tail, head, and tail, tail. And you're just interested in the probability that you don't have two heads in a row. If you have 2 heads in a row, that's the only possibility of getting 2 heads, right? Because you either, in other situations, you have at least 1 tail. So A2 is rather simple. A2 is just 1 minus p squared. The probability of getting a head is p. All right, 1. Okay. So A2, well, that's just the probability of, let's say, no head head. No head head is just 1 minus the probability of head squared, right? 1 minus p squared. So that's good enough for us. So A2 is 1 minus p squared. A2 is a function of p. When n greater or equal to 3, describe an using p an minus 1 and a n minus 2. So that was what I was thinking. You try to establish a difference equation. Let's think about the meaning of these quantities. So if you n is greater or equal to 3, n greater or equal to 3, so that means you've tossed the coin at least 3 times. An is the probability of what? An is the probability of no such thing as 2 heads in a row in those n attempts, in those n experiments, right? So let's try to draw a diagram here. So 1, 2, this can be head or tail, okay? We don't know. 1, 2, all the way to n. 1, 2, all the way to n. All right. So somehow we wish to connect an with an minus 1 and an minus 2. Of course, direct calculation is difficult. So how do we make that connection? An minus 1 means in n minus 1 trials, in the first n minus 1 trials, we don't have heads twice in a row. So this is n minus 2, so okay, n minus 1 and n. And n. Okay, so I think some sort of conditioning argument can be used here. If let's suppose the last one is a head, the last one can only be head or tail. So if the last one is a head, the nth trial is a head, and there's no head, there's no head there's no head twice in a row in all these attempts. Okay, so let's say the last one is a head, and in all these n tosses, there's no such thing as head twice in a row. Then what should the situation in the first n minus 1 tosses look like? Well, n minus 1 cannot be head. This has to be a tail. If this is the head, then the pattern, then what we want is not achieved. If the last one is a head, then the second last one must be tail. And in all of those tosses from 1, 2 all the way to n minus 2 cannot have two heads in a row. Okay, so that's the first case. That's the first case when the last one is a head. And we just repeat this analysis, but for the last one being a tail. If the last one is a tail, then what? Then it's impossible to have a head-head 2 times in a row, and it's not then it's impossible to have 2 heads in a row for the last 2 trials. It's impossible now. So in that case, you just need the first n minus 1 trials to not have heads twice in a row. That makes sense? So that's the conditioning argument here, because when you have when we do conditioning, I wrote down the conditioning formula earlier. When you do conditioning, you have to exhaust all the possibilities. You have to exhaust all the possibilities. So I'm conditioning based on the outcome of the last trial. So the last trial can either be head or tail. That exhausts all the possibilities. Okay, so let's write down the verbal analysis. So we consider 2 cases. So suppose we observe no heads twice in a row. Okay, we observe no how should I put this? No 2 heads in a row. Okay, we suppose we observe no 2 heads in a row in n tosses, n greater or equal to 3. All right, we consider 2 cases based on the outcome of the last toss. Okay, case 1. Case 1. The last toss is a head. The last toss is a head. All right. This means the second last toss, the last, i.e. ends, i.e. the ends. Okay. The ends toss is a head. Then what happened? As we mentioned, then the m-1's toss must not be a head, must be tail. And the first m-2 tosses must not have two heads in a row. And the outcome must not have two heads in a row. So that's case 1. Case 2. Case 2. The ends toss is a tail. Right, then it's impossible to have a head at the very end. Then the first m-1 tosses must not have two heads in a row. That's it. Okay, so now we're using this law of total probability. The formula is here. You have two cases. So here PA1 refers to the probability of case 1. And here PA2 refers to the probability of case 2. So PA1 is the probability of the last outcome being a head. And PA2 is the probability of the last outcome being a tail. And we need to figure out these two conditional probabilities. So given that the last outcome is a head, how can the original event happen? And what's the probability for that, right? So that's the law of total probability for events. By the LTP for events, right? So this is a perfect example of solving a difficult problem using conditioning. AN equals the law of total probability. AN, that's the quantity of interest, right? So case 1, the ends toss is a head. What's the probability of a head? Well, it's P. So it's P times A M. Actually, sorry, P. That's P. We need the probability of what? m-1 toss must not be a head. So P times 1 minus P. So this corresponds to the m-1 toss is not a head, and then times A m-2. Law of total probability. In the next case, well, the ends toss is a tail that has a probability of 1 minus P, and then times AM-1. Done. So that's the recurrence relation we're looking for. And now it just becomes a problem in discrete mathematics or algebra to solve this recurrence relation given the initial conditions, which there is a general theory, about which there is a general theory. So probability theory stops here. The rest is algebra. Okay, let's continue. When P equals 2/3, obtain all the pairs alpha beta of real numbers that satisfy the following recursions. So we're doing algebra now? Yeah, as mentioned, this has nothing to do with probability anymore. Part 3 is just manipulating the difference equation. So what we're trying to do is to create a geometric sequence. Geometric sequence defined as an plus alpha times an minus 1. You see, this is a geometric sequence with a common ratio of beta. You just need to find the right alpha and beta. All right. I guess the question does not assume that the test takers or whoever doing the exercises does not know does not know the details of the general theory of difference equations. This is a difference equation. Okay, let me put that down. This is a second order linear homogeneous difference equation. Okay, and it has a good deal of parallel between the theory of difference equations, especially linear difference equation, and the theory of linear differential equations. Okay, so before doing part 3, which we will follow, okay, this is not necessary, but I mean, we can at this point already solve the question. Well, to solve this, to solve this, you would use something called a characteristic equation. Once again, this is pure algebra. It has nothing to do with probability anymore. So to solve this, we can just solve them like differential exactly. You use the characteristic rules. To solve this, we use a trial solution. We use a trial solution. An equals r to the n. N equals r to the n. Of course, this needs to be scaled properly. This needs to be scaled properly so that it is a probability. But here we're just looking for the structure here. An equals r to the n for some constant r. Okay, and I guess the formulas will not be very pretty, but that's okay. So r to the n on the left hand side, just substitute and try to find r. Right. And p times 1 minus p, r to the m minus 2 plus 1 minus p times r to the m minus 1. Okay? What we can do is we divide by r to the m minus 2 on both sides. This way n cancels. So divide by r to the m minus 2 on both sides. Left hand side becomes r squared. Right hand side is p 1 minus p times 1 minus p times 1 plus 1 minus p times r. And this is a quadratic equation in r, which we can solve. Okay, I will not write the quadratic formula, but you know the idea. So p is now in principle solved. So r is now in principle solved, and r should have 2 roots. Let's check that. Okay, by the way, let's check that because there are different possibilities. So let's check the discriminant. Okay, big delta discriminant of quadratic equation 1 minus b squared minus 4ac is 1 minus p squared, 1 minus p quantity squared plus 4 times p plus 1 minus p. Okay, so rearrange, not rearrange, but factoring, you get 1 minus p times 1 minus p times 1 minus p plus 4p. Yeah, plus 4p, which gives you 1 plus 3p. So this is positive because p is between 0 and 1. So this is positive, which means it has 2 roots. So an has 2 roots. An has 2 forms, right? And the general solution is a linear combination of the two. You have a linear combination, and then to solve for the constants in the linear combinations, you use the initial condition, and the problem is solved. It's just that here we're not doing the general cases because the ugliness of the roots. But in principle, this problem is already done. But anyway, The question does not seem to assume that the reader knows about this. So instead, we are going to use something more primitive. Okay, we're trying to construct a geometric sequence from scratch, which is okay, which is certainly something we can handle. So suppose P is, let P, okay, let P be 2/3. Okay, then we have the recurrence relation or the difference equation for an in part 2 reads, okay, so you got 2/3 times 1/3, which is 2/9, plus 1 times 1/3. Okay, yeah, and now we need to do some shenanigans to construct the geometric sequence. So let's just use this form and expand, compare the coefficients, so we don't have to guess. Okay, we want an plus alpha an minus 1 equals beta an minus 1 plus alpha an minus 2 quantity. All right, let's go. So we want to rewrite this as an plus alpha am minus 1 equals beta am minus 1 plus alpha, okay, am minus 2. Okay, so we're just going to expand and compare coefficients. This is equivalent to an equals beta minus alpha am minus 1 plus alpha beta an minus 2. Okay, so that's just expansion. So now we need beta minus alpha to be 2/9. So we need, and alpha times beta to be 1/3. Can we do that? Can we simply solve that by inspection? I mean, this is a quadratic equation. Worst case, we're just going to solve a quadratic equation, so not a big deal. But can we inspect? So let's say if, I don't know, I don't think I can inspect. All right, let's not inspect. Let's just do the elimination. And oops, my cat is here. She wants to play. Oh. So alpha times alpha is what? Alpha is what? Alpha. Let's substitute what? Let's substitute, say, beta. Beta is alpha plus 2/9. Oops. Now over 2 equals 1/3. Okay, so you got alpha squared plus 2/9 alpha equals 1/3. Okay, multiply 9 on both sides. 9 alpha squared plus 2 alpha minus 3 equals 0. Can we spot the factorization? I mean, I'm usually not very observant when it comes to those, so just going to brute force, use the quadratic formula. Minus b, that's minus 2, plus or minus the square root of b squared minus 4ac, b squared minus 4ac, that's 2 squared plus a 4 times 9 plus 3. okay, over what? Over 18 to 8, okay? So that's what? 18 minus 2, so what's the thing underneath the square root? You got 4 plus, so 36. 4 times 9 is 36. 36 times 3 is 100. Hang on, is that even a rational number? I hope the question gives us this nice number to get something rational, huh? Do we have that? P is 2, sir. I want to check from the beginning. I hope this is a rational number so we can make our lives easier. Is it possible? So P is 2/3. 2/3 times 1/3 is indeed 2 nines, and this feels okay. And that's the form we want, right? Expand, compare coefficients. Beta is alpha plus 2 nines, all right. Multiply 9 on both sides. Yeah. Minus b plus or minus b squared minus 4ac, so it's 4 plus 4 times 9 times 3. 9 times 3 is 27. 27 times 4 is what? You know what? Let's use a calculator because I don't trust my math. 108 and n plus 4 is... That's not a rational number, huh? All right, that's a bummer. Divide by 4 is what? 28. Divide by 4 is what? Is 4. So you get a square root of 112, which is 4 times square root 7. All right, that's a pain in the butt. Okay. And the thing is, we don't need both roots, no? We don't need both. We just need a way to write this as a difference equation. Sorry, we just need a way to write this as like a geometric sequence where a n plus alpha, a minus a of m minus 1. Okay, so yeah, don't be annoyed or discouraged by this seemingly disgusting algebra because the probability part is over. This question I'm doing right now, okay, whatever is shown on the screen has nothing to do with probability, it's just sheer algebra. All right, so this is alpha. If we pick alpha to be, say, with the plus sign, okay, it doesn't matter, okay? You can pick your negative sign, that's totally okay. You just need one such combination of alpha and beta so that this works. We don't need to write all the combinations, no? Oh, all the pairs. We need all the pairs, actually. We need all the pairs. We actually do need all the pairs. Fair enough. Okay. So this is alpha. So alpha has 2 roots, and beta has 2 possibilities as well. All right, so beta is what? Beta is alpha plus 2 nines. Okay, beta is alpha plus 2 nines. And then you got what? It's ugly, but what the hell? Right. That's it. Okay, that's alpha and beta. Okay, so, and whenever alpha picks a positive sign, beta is a positive sign. Okay, so that's all the pairs. That's right, alpha beta equals, this is alpha and this is beta. So there are two pairs, okay? Sorry, there are 2 pairs, not 4. So that's the combination. Okay, and now we can write an as a function of n. This is going to be painful because of the ugliness of these formulas. Okay, but yeah, as I said, this has nothing to do with probability anymore. All right, so then since from part using the pairs, using any either pairs, okay, either pair of alpha beta from part 3. We get that an, you can immediately write down the general formula for this. This is what? This is, okay, if we're doing this silly method instead of the more general method, here there's a bit of a pain because you now have what? Well, I guess you can, well, you anyway, from the pairs, from the pairs of, sorry, I take back what I just said. We have to write it this way. This is A2 A2 plus alpha A1 times what? Times beta. Beta is the common ratio. Yeah, beta here is the common ratio raised to the what? n minus 2 or n minus 1? All right, so when n is 2, when n is 2 on left, you should get A2 plus alpha A1. Right? When n equals 2, the left-hand side should be an, that is A2 plus alpha A1. But here, you would have A2 plus alpha A1 times beta, and that's not good. So you use beta to the n minus 2 instead. This way, the equation is consistent when n equals 2. So now it's just a matter of evaluating these. Okay, A2 is given, A2 is p squared. I recall that A2 is p squared. No, it's not p squared. A2 is 1 minus p squared. So it's 1 minus p squared. P squared is 9.4. So it's, yeah, this is a constant. Okay, it doesn't really matter. Okay, so here A2, let's compute A2 plus alpha A1 is what? A2 is 1 minus p squared, so it's 1 minus 4 ninths plus alpha. Let's just write alpha as such times A1. Well, A1 is 1. Yeah, A1 is 1. So here, that's it. So you get 5 ninths plus alpha. Okay, this is 5 ninths plus alpha times beta to the n minus 2. Okay, and because there are two combinations, right? There are two combinations of alpha and beta. Hopefully we can do some shenanigans there. Use the two pairs. Okay. The first pair, alpha, let's say first pair we use a plus sign. Alpha and beta both are plus sign. Okay, plus sign here, plus sign here. Hang on, this doesn't look right. Okay, there should be a minus sign here. Plus sign here. Okay. Beta is also a plus sign, like so. All right. So that's it. So that's the first pair. And then you got the second pair, where you put a negative sign in front of the 2 minus square root 7, like so. And what we do, well, to get an, you simply eliminate an minus 1. I think there was a sign flip in part 2, but I'm not sure. Sign flip? This is the equation for alpha, right? And this is what we got from quadratic equation. Beta is alpha plus 2 nines. So whenever alpha picks up a positive sign, beta is also a positive sign. So you should be plus minus instead of plus minus minus plus. Whenever alpha use plus, beta also use plus. So I don't know why they set up this. I thought when they're giving us a nice, when they were giving us a concrete number for p, you would have rational roots, so everything gets easier to calculate. But this is still disgusting, right? So now it's just a matter of eliminating an minus 1. Subsection 2 of this question. Subsection 2 of this question. In subsection 2 of this question, we're just using the law of total probability to establish a recurrence relation or difference equation. Right? This equation is correct, I suppose. I mean, I'm not supposed. I'm pretty damn sure this is correct because we listed the reasons. Right? Line 3. There, line 3. This line 3? The line I wrote? Case 1. Wriggle? I'll wait your response here. Is this what you're saying? Subsection 2 of this question. Next page. This one? An equals r to the n. That's the trial solution, right? This was what I was saying. If we finish this line here, so you should get, I'm just going to write down the sketch, okay? You should get R1 and R2 that are distinct roots because the delta is positive. Line 3 of that bit of algebra. Okay, let's try to verify this one more time. Let's plug in r to the n on both sides. Right, so an minus 2 becomes r to the n minus 2. N minus 1 becomes r to the n minus 1. We divide r to the n minus 2 on both sides. Left hand side becomes r squared. Right hand side becomes p times 1 minus p plus 1 minus p times r. Oh. Yeah, you mean this? Yeah. I was silly. Yeah. Does it affect the delta now? It's still b squared minus 4ac, right? Yeah, you mean this sign, right? There's a sign flip. Yeah, you're totally right. You're totally right. There's a sign flip. Yeah, you're right. Yeah, that's a stupid mistake. No, don't be sorry. Like I should be sorry for being careless. Okay? Yeah. So anyway, I'm not going to simplify things any further because this is kind of painful, but R1 and R2 are distinct, real, okay, real roots. So this means the general solution, like just following the same theory of second order differential equations, an has the general solution of the form, okay? an equals what? An equals big A, R1 raised to the n plus big B R2 raised to the n. Okay, because this is linear and homogeneous, so any linear combination of the trial solutions still gives you a new solution. And now use A1 equals 1 and A2 equals 1 minus p squared to solve for A and B. And now making sure what I'm doing, right? Being pedantic as no. Don't be sorry. Like, details matters. Okay, this is the kind of mistake that kills people in real life. Like, imagine I'm trying to design a spaceship and I mess up a sign. Boom, millions of dollars wasted, astronauts killed. You know, this is important stuff. One, thank you very much for pointing that out. 1 equals A R1 plus B R2. All right, and the second equation is 1 minus p squared equals A R1 squared plus B R2 squared. So that's it, right? You got a system of linear equations for A and B. So it has a unique solution. A and B are determined. So AN is fully determined. And that's it. So everything else here we're doing are just special cases. And here I'm not going to finish the algebra, simply say eliminate AN minus 1, you get AN. Okay? You can use this method or the method we sketched earlier to get AN. Okay, difference equation up front, yeah. And actually, you know what? You can solve it using linear algebra as well. You can set up a vector matrix equation that corresponds to the linear homogeneous difference equation. And it turns out to be an eigenvalue and eigenvector problem. Right? Right. So yeah, this is rather disgusting, but anyway, that's just it's irrelevant. It's irrelevant, right? So this part, like part 2, is really beautiful, in my opinion. Right? And after you set up the difference equation, the rest is just brute force algebra. Right? So anyway, so let's get to this is part 4, part 5. We're doing part 5 now. Okay, part 5. Because we haven't touched B, right? Haven't touched B. What about B? I think we should use the same line of thought to establish the difference equation. Okay? So how do we do that? First, let's obtain B3 as a function of P. B3 means what? B3 means the probability of the coin never comes up heads 3 times in a row. So no heads 3 times in a row, and the total number of trials is 3. So you're just excluding head, head, head. Right? So immediately B3 is the probability of no head, head, head in 3 tosses. So that's 1 minus p cubed. Simple. All right, so B3, by definition, is the probability of no head, head, head. Right, so it's 1 minus p cubed. Done. All right, so once again, difference equation times. So this is a third order difference equation. Right, so this is a third order difference equation. You know what's funny? This is not a very nice number either. Like part 7, you can see it's not a very nice number either. But I find it funny that for the second order difference equation, the question the question does not assume you know the theory of linear difference equation, and instead guide you through how you would solve it using this trick. Okay, construct a geometric sequence from that. Okay, right? If it assumes that you know the theory of difference equation, why would it suggest this form, right? Apparently, it does not assume you know the theory of difference equation for the second order difference equation. It does not assume you know that. So it set up this hint because part 3 makes it look like a geometric sequence. And what's funny is that in part 7 it just says screw it. So screw it. This is the formula. Or I don't know why. Perhaps they just want you to set up the difference equation and then plug this in and show this Bn satisfy the difference equation as well as the initial conditions. I mean, that's what's the point, right? This is supposed to be a probability question, not like a tedious exercise in complex numbers, right? Anyway, I don't know. I don't know which country, like what sort of exam is this? Vizzy, do you mind enlightening us a little bit? Where did you find these questions? I'm interested. I'm honestly curious. Is this Indian exam or I don't know Japanese exam? The last exam you got me was Japanese, which was fun. But anyway, um, I'm not going to bother with this formula. Okay, I'm not going to bother. I'm simply not going to bother. But instead, I will set up the difference equation, and I will outline the same method for solving the difference equation here. Essentially the same method, but here you're using the third order situation. Okay, cool. Um, part 6. Part 6. When n is greater or equal to 4, describe Bn using P, Bn minus 1, Bn minus 2, and Bn minus 3. Okay, so let's set up the same diagram here. Let's set up the same diagram. So you got 1, 2, blah, 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 2, m minus 3. That's the index of the trials, okay? M minus 2, m minus 1, and n. So inspired by part 2, let's consider 2 cases for the last, for the last trial. If it is a head, then what should be going on for the previous trials? Well, you don't want 3 heads in a row, no? You don't want 3 heads in a row. So given that the last one is a tail, given that last one is a head, we need 2 tails before the last head. Or no, actually, you just need to destroy the pattern of head, head, head. Right? So there are more possibilities. Yeah, you can get head, tail, or tail, head. Or tail, tail, too. Right? Or tail, tail, too. So you can have tail, 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 head, or head, tail. Remember, if you only have 2 heads in a row, that's still okay. So what this means is, so we got to be a little bit careful here. Let's look at, so there are 3 situations, right? These are 3 situations. Let's think through them one by one. From bottom to top. Let's say the last 3 are tail, tail, head. What's going on in the first n-1 trials? Well, you just, because what's the n-2 toss is a tail. You just need the first n-3 tosses to not have 3 heads in a row, and that's fine. No head, head, head over here. If there's no head, head over here, and there's no head, head over here, what about the intersection? Okay, what about the intersection of these 2 segments? Okay, I'm not talking about intersection, but rather the connecting parts. Well, you got a tail, tail here, right? You got a tail, tail for these 2. It doesn't matter if n-3 is a head or a tail. Head, head, head can never happen. Okay, and if let's say I'm looking backward from n minus 2, I know this is a tail. Well, once again, it doesn't matter. It can be any two combinations, any of the any combinations for the last two. Okay, you know what I mean? You can have head, 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 tail, 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 head. Who cares? So for the last case, okay, for the last case here, meaning the last three are tail, tail, head. If that's the case, you just don't need head, head, head. You just need to have no head, head, head among the first n minus 3 trials. That will be good. That'll be it. All right. And I think the same can be said about the second last situation where you have tail, head, head for the last 3 trials. Because the last three are tail, head, head. Right. This is a tail, so it kills the possibility of getting a head, head, head this way. This is impossible. So you just need no head, head, head. Once again, you just need no head, head, head in the first n minus 3 trials. But the first case is different. The first case starts with an H. So even if there's no head, head, head here, if you have a head, head at the very end, this is a 3 heads in a row. Right? So the first case is where things are tricky. We need to have no head, head, not just no head, head, head. That makes sense? You must rule out head, head as well. And not just no head, head, head. And no head, head, no two heads is already enough, because if there's no two heads in a row, there can be no 3 heads in a row. Right? So that's the situation. Okay, so here, this means you would have no head, head. That's a probability of an minus 3 times the probability of those two possibilities combined. Okay, so what's that? So those two has commonalities. So those two, what does those two have in common? Well, we can combine those two possibility as n minus 2 is a tail, n minus just n is a head, and n minus 1 has no restriction. Right, so that's just tail, which is 1 minus p, times 1 times p. So an minus 3 times 1 minus p times p is the probability of those two situations. And on top, you would have head, tail, head, which means is a p squared times 1 minus p times an minus 2. All right? So that's it. Okay, what else? What else? Well, we analyzed the situation where the last one is a head. Okay? And then let's figure out the other situation. Let me just draw it here. Okay, 1, 2, all the way to m minus 3, m minus 2, m minus 1, and n. So let's imagine you only have a tail here. Right? So that's the opposite situation. If your nth toss is a tail, and that's very easy, right? Because you just need the first n minus 1 to have no head, head, head. Because the last one being a tail kills the possibility of having something like a head, head, head at the very end. It's impossible now. You just need the first n minus 1 to have no head, head, head. All right? So this is just am minus 1 times the probability of a tail, which is 1 minus p. And sum all of these up, you get sorry, not a, it should be b, my bad. Bad notation, it should be b. So you sum up all these terms, you get bn. Mm-hmm. Okay. And then it becomes a silly algebra problem, which is kind of disgusting. I'm just going to, I'm not going to bother write down the details. Should I write that? Or should I leave that as an exercise? Should I leave that as an exercise to write down the reasoning like here? Okay, I'll leave that in the exercise. The reasoning is left as an exercise for writing, okay? Try to express the ideas verbally. But I'm going to put the diagrams here as hint. So this is the diagram. Is it possible to select these? Apparently impossible. So yeah, I'm just going to write it this way. So the last one is a head. Okay. Okay. So that's the case. You have tail, 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 head, and head, tail, tail, head, tail, head. Okay. So here is no head, 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 no head, 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 no head, head. Okay. This is case 1. Case 2 is a lot simpler. If the last one is a tail, you just need to have no head, head, head among the first n minus 1 trial. Okay, the exercise is to organize this diagram into sentences, complete sentences. Okay, so Bn is, let's write 1 minus p, so that's case 2, 1 minus p times Bn minus 1, Bn minus 1 plus, here you would have, this is Bn minus 2, this corresponds to Bn minus 2, Bn minus 2 times what constant? The probability of 2 heads and the tail, so you get p squared 1 minus p. Good. And the last one is you need a coefficient times Bn minus 3. What's the coefficient? Well, you need a head and tail. So you just use p times 1 minus p. That's the full equation. All right, so that's the full equation. And now what do we do? Once again, you set up the difference equation, blah, blah, blah. Okay. I like how in part 7 you simply just the question just simply gives up and stops giving you a hint of how to solve a difference equation and assume you know the stuff. Okay. Anyway, this is funny. Honestly, I don't think this is fair. As an exam question, this is supremely unfair. But okay, the third order linear homogeneous difference equation, because you either assume the test taker knows the theory or don't. Like, what is this? Um, anyway, Bn equals r to the n. Okay, remove this. This is third order equation, huh? The third order equation. So what should we have here? R to the n, and then r to the n minus 1, r to the n minus 2, and finally r to the n minus 3. Huh? Okay, and then we divide by r to the n minus 3 on both sides. You get r cubed. R cubed equals what? Equals 1 minus p. So it just now becomes a cubic equation problem. Has nothing to do with probability anymore. And it's r plus p times 1 minus p. Yeah, that's it. That will be it, right? So, and let's not make the same mistake. I mean, I will not make the same mistake when we flip the sign. So we get a minus here. Everything becomes minus. All right. Okay, so let's use the special value since here p is what? P is 2/3, huh? Let's use p equals 2. Oh, sorry, not 2/3, but 3/4. P is 3/4. P is 3/4. So this simplifies to. Okay, this cubic equation simplifies to r cubed minus 1/4. All right, p squared, that's 9/16 times 1/4, so it's 9/64. Okay, p times 1 minus p, so that's 3/4 times 1/4, so it's 3/16. All right. Okay, so now let's multiply everything by 64. You get 64r cubed minus 16r squared minus 9r minus what? 3 times 4. Pain in the bottom, exactly. Like, come on, this is a probability question. Like, anyway, by the way, just as a tip, do you guys know how to find a rational root from this? There's something called the rational root theorem. There's something called the rational root theorem that says if this equation has a rational root, which is by no means guaranteed, if it has a rational root, I haven't used that for decades actually. I haven't used that since I left high school. The rational root in the form of p over q should have this form. P, I think p should divide, the top should divide the constant, and the bottom should divide the leading coefficient or something like that. I mean, I can't really remember, but there we go. Let me find the rational root theorem. Yeah, this is the rational root theorem, huh? Yeah. There you go, Wikipedia, rational root theorem. This is like a basic result in high school. So here you have a polynomial equation, okay, with integer coefficients. So if you each rational solution, by the way, this is by no means guaranteed to exist, but if it exists, okay, each rational solution of the form P over Q, written in the lowest terms, P is an integral factor, so P should divide the constant. Yeah, top should divide the constant, and bottom should divide the leading coefficient. Okay, so now you just need to enumerate. So this is a stream on high school algebra now. So 12 has factors. 12 have factors of what? Hang on, and it should be in lowest term, right? P over Q should be in lowest term. 12 have factors of 1, well, plus or minus 1, plus or minus 12, plus or minus 3, plus or minus 4, and plus or minus 2, and plus or minus 6. Right? That's 12. And 64, oh God, 64 has so many factors. So the rational root theorem is supposed to narrow down the possibility of rational roots, and then you can divide that rational root so the cubic equation becomes a quadratic equation, and then boom. Okay, 64 has factors. Well, I don't even want to write those down. This is painful. My goodness. All right. Vizzy, I hope this is not your actual exams in your country, because if that's the case, those people are psychopaths. My goodness. Because this is pure luck, right? Imagine having a 90-minute, and this, you know what, this has nothing to do with mathematics. Mathematics is never about speed. Because, I mean, when I grew up, like, the teachers and parents, they humiliate kids for not being able to do the mental math fast enough. Like children were asked to do like just multiplications by in their mind, and if they're not quick enough, they were reprimanded, and sometimes corporal punishment. You know, this all sorts of disgusting things. Yeah, I'm still alive. I'm still alive. I'm doing the questions. Why I'm not alive? Why I'm not alive? Yeah, and we're nearing the end, by the way. And if you guys want to stick around, I'm gonna do something random. I'm gonna show how to calculate the ballistic table of a pistol round. How about that? Just as a reward. Anyway, so yeah. So these are all the possibilities. I guess you're supposed to hang on. You're supposed to enumerate all the combinations of P over Q among these, and then figure that out. But anyway, I'm not going to bother. I'm simply not going to bother. Okay, it looks like the rational root is 3 over 4. That looks like the rational root. And after that, after dividing that root, okay, let's do the division. Okay, let's do the division. So so after trial and error, so that's in principle can be done, but I don't know, like if you're unlucky, let's say, if you're unlucky, you choose the wrong combination during the exam, then you're completely screwed. After trials and errors, okay, I'll just say that the rational root is, or a rational, you just need a rational root, right? 3 over 4 is a rational root. Is a rational root, because I'm just going to assume that and skip the painful steps of trials and error. Is a rational root? Yeah, after sheer dumb luck, exactly. You are absolutely right. Imagine someone, like two people with equal skills on an exam, and the first guy figured out the 3 over 4 during his first trial, and the poor second guy spent like 8 trials and couldn't find that because there are more than 8 trials in total, and guess what? It has nothing to do with mathematics anymore. It's just sheer dumb luck, exactly. Like, anyway, the question itself is extremely unfair, to be honest. I mean, if that's supposed to be an exam question, that's extremely unfair. So we got the coefficients: 64 minus 16 minus 9 minus 12. Okay, so enough for the rand. I think you guys know what my points are. This is not a rand channel or a drama channel. We're here to do math. 16 minus 9 minus 12. All right. So we're using the synthetic division method. We're using the synthetic division method. I haven't used that for ages because I haven't manually solved a cubic equation for years. 3/4. Because why would I? I just ask the computer to do that for me. If you pull down to 64 unchanged, 64 times 3/4, that's a 48. That's a 32. 32 over 4 is 8. 8 times 3 is 24. 24 minus 9 is 15. And that's a 12. So that's exactly, which confirms that 3/4 is a root. Okay, so this means that you have a factorization. Oops. Therefore, there's a factorization. This is p minus 3/4 times what? 64. The coefficients are 64, 32, and 15. So 64p squared plus 32p plus 15. And then you just calculate the complex roots. So for the complex root, you use the Euler's formula to reduce that to sines and cosines, basically. So delta goes b squared over 4ac, so 32 squared minus 4 times ac times 15. I'm going to use a calculator for that. All right, 32 squared minus 4 times 64 times 15. Hang on, why is it negative? Oh, right, it should be a complex root, that's why. But can you imagine doing this? Even after you spend all that time, after figuring out the rational root, you still have to deal with this garbage. But my goodness. All right. Let's just double check, okay? Just double check. 32 squared. 32 squared minus 4 times 64 times 15. I swear this is possibly, I mean, in retrospect, a lot of people hate math. It's because of crap like this, right? And it's sad because it has nothing to do with math. Yes, it has something to do with numbers, but the way we punish and reward people based on these nonsense is not math. I think we can all agree with that, right? Okay, so let's divide that, say, by 64. We get what? 44. Okay, so let's keep dividing that by, so it's 64 times 4. 64 times, so 64 is 8 squared. 4 is 2 squares. That's 16 squared. 16 squared times 11, huh? So this is what? Minus 16 squared times 11. Just to double check that. 16 squared times 11 is this. Okay, that's great. So that means the complex roots are p equals to plus or minus, that's what, plus or minus minus b, that's a minus 32, plus or minus 16, 11i, right? And then over what? 2a, which is 2 times 64. So this can be simplified to minus 32 cancels, it gives minus 1. Actually, no. You can only cancel a minus 16. So minus 2 plus or minus of what? This is 4. Sorry, square root of 11i over 4. No, not 4, but 8, right? Yeah, 8. So where does the cosine of 1 over cosine equals 1 over 3 comes from? Huh? I think there's a mistake here. There's something wrong with our solution. Because this is not what we're looking for, huh? Hang on, there might be a big mistake actually. There might be a big mistake. But somehow we still managed to get this correct root. Is there a mistake here? Seriously, is there a mistake here? Let's try it. Because I'm kind of paranoid because this does not look like the answer at all. This does not look like the answer at all because we are not getting this complex root and we're not getting the cosine of 1, cosine equals 1 over square root of 3 thing. Let's reconsider. Yeah, this is right. Head, tail, head. Okay. Let's just double check here. So here you got tail 1 minus p times p squared. Here you have 1 minus p squared times p. If we add them up, what do we have? We have, if you add them up, you got a common factor of 1 minus p times p and p plus 1 minus p, which is 1. Yeah, so that's right. Did we make any mistakes here? This is 1 minus 4. 1 over 4. Times 64. Oh, actually, yeah, this is correct. This is correct. Times 64. This feels okay. And we got the 3/4 as a rational root. Did we? I don't think we made a mistake here, no? Hmm. You know what? Screw that. That's AI. I'm gonna AI this. I'm just gonna AI the cubic equation part. All right. Because I have no patience for the cubic equation thing. Okay, let me just put the question in another screen. So solve the cubic equation. 64 r to the third minus 16 r squared minus 9r minus 12 equals 0. This is where the ChatGPT or whatever AI you're using tends to make the most mistakes, because they can write an essay but they can't count. They're notoriously inaccurate. Okay, wow, what a weird method. I'll use the Cardano's formula. What the actual? Are you serious? Okay, um, I think ChatGPT has just gone full idiot mode. Let me just okay check whether 3/4 is a root. 3/4 is not a root. What? Then what happened here? What happened to synthetic division? Hang on, 3/4 is not a root. Am I stupid? This calculation is correct, no? Let me recheck that. Okay, 64. Pull it down. 32. 32 over 4 is 8. That's times 3. That's 24. 24 minus 9 is 15. Hang on. This is the equation, no? I just got here waiting for this video. Unfortunately, you are in the most irritatingly painful part. I mean, this is you missed the good part, man. You gotta watch the recording. This is just aggravatingly stupid because we're trying to solve a cubic equation, and it's supposed to be a probability question. All right, I guess such is life. The numerical solution, it's not supposed to be a numerical solution. That's an exact solution. We just verified it using the synthetic division, for Christ's sake. All right, so let's try something else. ChatGPT can go screw itself. All right, so let's try synthetic division calculator. Synthetic division calculator. Right. Okay. So let's see what's if this should be the correct cubic equation, because I was getting paranoid. 64 times x cubed minus 16 x squared minus 9 x minus 12. All right? No, 64, not 63. The x minus 4/3. Sorry, not 3. What's going on? 4. Yeah. Yeah, 60. Yeah, this is my step. This is synthetic division, you see? 64 minus 16 minus 9 minus 12 in the first row. Okay? 48, 32, 24, 15. Hang on, what's going on? Oh, I was stupid. This doesn't work. 15 times, this doesn't cancel. This does not cancel. It does not freaking cancel. So there must be a mistake in this cubic equation. Let's reconsider this one more time. Let's reconsider. Okay, so 4 over 3 was not a root. So this reasoning needs to be reconsidered, needs to be completely reconsidered. So describe Bn using P, Bn minus 1, Bn minus 2, and Bn minus 3. Let's consider the last outcome. All right, so by the way, who just got here? The Ayadkar. Okay, sorry for butchering your name, but let me just go through the problem setup one more time. A coin with a probability of coming up head equals to P is tossed n times. Let An be the probability that the coin never comes up heads twice in a row. This means in all n trials, okay, you would observe a sequence of outcomes: head, tail, head, blah, blah, blah. Okay, in those sequences, you don't observe 2 heads in a row. And the probability for that is An. And by the way, we already answered An, sort of, mostly. Okay, we didn't actually solve An because the numbers are too ugly. But that's not the point. The point is we're dealing with Bn. Bn is the probability that the coin never comes up heads 3 times in a row. So you're considering the sequence not having a head. That's not allowed. Okay, we're interested in the probability of that. So we're trying to set up a difference equation in Bn and then use the theory of difference equation to solve it. Okay, so that's it. So that's part 6, actually, setting up a difference equation. Our idea was to condition on the last outcome, or at least first conditioning on the last outcome. If there's more situations to consider, we will do so. So if the last outcome is a tail, what would the outcomes in the first n-1 trials look like? Well, you just don't have a head, 3 heads in a row among the first n-1 trials. Because the last one is a tail, it's impossible to get head in the last 3. In the last 3 trials, so that's not possible. So you just restrict the first n-1 trials to not have head. So that's one possibility, relatively easy to handle. And by the way, when this happens, this would have and this event has a chance of Bn minus 1 times 1 minus p to occur, because the last one, the tail, has a probability of 1 minus p. Right? And given the last one is a tail, the probability of having no head in the entire sequence is simply the probability of not having a head in the first n-1 trial. So it's Bn minus 1 times 1 minus p. So I think that's done. So now let's consider the next situation where the last outcome is a head. Okay, how do you avoid head if the last one is a head? Well, if the last one is a head, that means the third last and the second last cannot be head simultaneously. So you have three situations: head, tail, tail, head, and tail, tail. And let's consider from bottom to top. In the last two situations, where you have a head, okay, where you have a head on the trail n minus 2, you just need to not have three heads in a row in the first n minus 3 trials. And this would completely avoid head, head, head in all the trials. However, for the first case, if you don't have if you don't have head, 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 that's not enough. Because if you have two heads in a row, if you have two heads in a row, hang on, this is sus, huh? I think this is sus. This needs further consideration. This needs further consideration. I'm trying to say is this seems to need further consideration. You can still have head, head in the beginning. You just can't have head, head at the end, right? Rigo, are you with me? Because no head, head, this is too strong. This is way too strong. Because indeed, this will guarantee that you would not have a head, head, head. You can still have head, head at the start, at the beginning. You just need to avoid head, head at the very end. You just need to avoid head, head at the very end, no? You cannot have head, head at n minus 3 and n minus 4. That's what I'm trying to say. You can still have two heads in the beginning. So what's the new restriction here? So let's say if your last three is head, tail, head. You just don't have head, head at the end. I do not know how to encode that, right? That's the problem, right? I'm struggling here as well. And the problem is, I think this is wrong too. This is wrong too. So our original reasoning, which turns out to be false, says, okay, I don't want head, head in the first n trials. And that's not even a bn minus 2. I don't even know where we got this from now. That's not even a bn minus 2 because bn minus 2 says there's no three heads in a row in n minus 2 trials. But here we're trying to encode that there's no head, head in what? In n minus 3. That's not bn minus 2. So this is actually wrong. All right, so this part needs some further consideration. This part needs some further. If, let's say, I'm just concentrating on this case here. So if the last three is head, tail, head, if the last three is head, tail, head, and I want to avoid head, head, head in the whole sequence, well, I cannot have, yeah. So you need no head, head in what? In from 1 to, so let's redraw this, okay? This is head, tail, head for the last three, and then in n minus 4, n minus 3, n minus 4, n minus 3 cannot be head, head. Can we try enumerating all 8 possibilities? Hang on, you just don't need no head, head here, right? No head, head, that's enough. You can have head, tail, tail, head, tail, tail, and those are okay. And no head, 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 no head, head, head for what? For m minus 5? But this would require bm minus 5. You need bm minus 1. I mean, bm, you can't go, in recurrence relation says you just need bm minus 3. I don't know, like, I'm totally confused here. Should we AI? It's getting late, should we AI? You know what, screw it, let's AI. I think we give a fair shot. Huh? This feels weird, yeah. Let's AI. Sorry for that. So how do we formulate the question? Oops. How do we formulate the question? Well, let's just say, let's copy the setup here. Okay, consider a coin with the probability of coming up as equals to P. Toss the coin n times. Let Bn be the probability. Yeah, just grab the first paragraph. Be the probability. We don't need the full first paragraph, no? Be the probability that the coin never comes up. Can this problem be described as a Markov process? I think so, yeah. I think it's possible to get a Markov chain, no? Let me just put it down, okay? 3 times. Because it's kind of getting late. I'll ask AI for that, okay? 3 times. But we will audit the process, obviously. Define B1. So, eternal. I think what you're trying to say is we are considering the states of consecutive we're defining the states of a Markov chain as consecutive outcomes in 3 tosses. And head, head, head is considered an absorbing state. You're asking about the probability of never being absorbed in n trials, right? So that's the description. So so you have 8 states in total. Head, 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 tail, head. You just do the usual numeration, right? And so we're considering the transition. Let's say if you have tail, 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 the next state can only be tail, 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 or tail, tail, head. So that's the next state. So you can set up a transition matrix that way. And the state head, head, head is something that we don't want. Right? So we designate that state to be the absorbing state, which means if the Markov chain hits that state, it's dead. It stops. It just stops. Okay, and we wish to calculate the probability of the Markov chain not being absorbed within n steps. Yeah, so the problem can indeed be described by a Markov process, but I doubt it will have a nice analytic solution. Instead, you'll get a matrix form and you have somehow to show this is equivalent to the answer is given. So it's a pain in the butt. But in principle, I think it can be done. Right, so define that, establish and recurrence. No, it's a finite chain. It's a finite chain. It has 8 states. It's not infinite. It's got 8 states because we're defining the state to be the most recent outcomes of the 3 tosses. So it can only be 8. So it's not an infinite state Markov chain. Is that what you mean? Establish and okay, I'm just gonna keep typing. Establish and a difference equation for Bn for n greater or equal to 3. N's in the tail, yeah? Okay, it's just Q, Pn minus 1. We got that. N's in the head tail. Guys, let's compare our reasoning with AI. End of its tail, Bn minus 1 times Q. The AI denotes 1 minus P as Q. So there's that. Ends in the head tail. End in the head tail, huh? Hang on. If it end, the first n minus 1 tosses may be any admissible sequence. Wait. Why can't the, is AI retarded? Sorry about the language. My bad. Why what is this? Why can't the last one be head, huh? So according to any with no head must end with one of the following with mutually exclusive ways. Are you kidding? Why can't the last one be head? Yeah, you're stupid. My goodness. Sorry, but this is okay. The last toss is a head. The last toss is a tail. 8 states. Yeah, exactly 8 states. The last toss is a head. There's a tail. Okay. Yeah, this is right. The sequence ends with exactly one head. Tail head. Tail head. So here we're looking at this case and this case together. Tail head and tail head. So now for the first m minus 2 trials, you just have no 3 heads in a row, huh? The sequence ends with exactly one head. And the first m minus 2 tosses from any admissible sequence. Contribution. I'm navigating a way to try for myself. Lol. Thanks for the stream. Looking forward to the next one. Yeah. Bye, Kevin. Thanks for joining the stream. Yeah, I mean, you have to be extremely vigilant when you read ChatGPT because AIs are extremely confident in their tone. AI are usually like this. They're extremely confident in their tone, and that sometimes tricks you into believing it easily. So here we're seeing tail head at the end. Thus the first, thus the m, and the first m minus 2 tosses from any admissible sequence is fine. Okay, and then it ended with tail head head. There, that's it. That's the last one. Yeah, I think we were treating this as a separate case and over confusing ourselves. But instead, the better way, okay, it has to do with how we arrange the possibilities. This possibility really should be combined with the last possibility. Because if you got tail head at the end, it really should be based on the final few outcomes, right? So if you consider tail at the end, the next logical case should be tail head at the end, and then tail head head. We artificially separate those two cases and treated the first one as a special case, which is not. Right, so this is more like it. Now, this is more like it. Yeah. So that's the three cases. So that's the three cases. All right. So this is, I think we're on the right track now. Okay. So let's rewrite this. Okay. So there should be three cases. I will not use words, but just draw the diagram here. Case one. Case one. It ends with a tail. Case two. It ends with a head, but that's the only one. No. But that's the only one head at the end. So you end up with a tail head. Okay, that's the end. And case three. It ends with a tail head, like so. So you're gradually adding head. You're gradually adding head. So this we can do into some other time. No ballistics today, okay? No fun for today, actually. Use Gemini. I get more accurate math answer from there. Okay. Yeah, I mean, I never tried Gemini, actually. I don't know, but I don't want. I'm not bothered to do so today anyway. So I'll try Nova. Okay, Nova. I'll try the Gemini next time. But still. It can give intelligent answer. You just have to prompt it correctly, right? And be critical. So here we have m minus 3 trials at the beginning. And this can be anything, anything that is admissible, basically. M minus 2 and m minus 1. Okay, so that's the diagram. It's much cleaner. Okay, so we should get here it should be m minus 1 times p, 1 minus p times p squared. That's a tail head. All right, and then 1 minus p times p, bn minus 2. And lastly, just 1 minus p times bn minus 3. Okay, so now let's get rid of everything. Let's get rid of everything, and these aren't needed now. Okay, these aren't needed now. Okay, so let's just plug in here. Okay, yeah, we made a mistake here, which is critical. I made a mistake. Okay, I should really stop using we, because this is all my doing. Okay, I'm not trying to diffuse responsibility, because I mean, when you write math stuff, or when you write math paper, you always say we consider something. You never say I consider. It's just a culture thing. You don't use first person pronoun in math writing at all. You always say we consider, we do X, Y. You're dragging the reader into this. So I said, oh, we made a mistake. It's simply because of my habit, not because I try to blame it on the viewers, if you know what I mean. Anyway, so here, okay, so this is the cubic equation. Divide by r to the n minus 3 on both sides. You got r cubed equals 1 minus p squared, r squared, plus 1 minus r, well, just r, and plus 1 minus p. That's it. That's it. All right, so plug in numbers. P is use p equals 1/4. Okay. Actually, 3/4. So r cubed is what? R cubed. This is 1/4 times 9 over 16. So that's 9 over 64. 1/4 times 3/4, that's 3 over 16 right here. And lastly, you just got a 1/4. Okay. So let's turn this into an equation with integer coefficients. Flip the signs and be careful. All right, equals 0. Multiply 64. 64r cubed minus 9r squared. This is a brutal question. This is absolutely brutal. Minus 16. Question. These three cases logically sound more correct when you put the t at the last cell. Yes, exactly. Exactly. Because in my original thought, I misplaced the location and I thought, oh, this is special because there's an h here. But really, what matters is how many h you had at the end, at the very end. That's what matters. Okay. Anyway, we learned. I mean, I learned. I guess we learned together. And you can. I think I can cut myself some slack and say we learned. Anyway, so here we have this cubic equation. Let's just use the rational root, 4/3. Not 4/3, but 3/4. Okay, let's use synthetic division. Let's use synthetic division right here. And this way, and this time will be hopefully correct. 64 minus 9 minus 12 minus 16. The candidate root is 3/4. 64 get pulled down. 48. And this is what? 39? It's looking really bad, huh? Hang on. Is the equation correct? Looks about right, huh? Solve the cubic equation. 64 r cubed minus 9r squared minus 12r minus 60. . use the Cardano method. What the hell? Hang on, this is still not correct, huh? Yeah, I was stupid. I was stupid. This is n minus 1. My goodness. It's getting late, huh? Or I'm just stupid. I should really stop making excuses. This is m minus 1, m minus 2, m minus 3. All right, let's start over. Let's start over. This is embarrassing for me. Okay. 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 Much better. Minus 1, and minus 2, and minus 3. Okay. We can do this. Okay. This is near the end of the tunnel. Okay. Divide by r to the n minus 3 on both sides. R squared, r constant. Okay. This is r cubed. Okay. Use the value of p. Use the value of p, so this is 1/4. 1/4 times 3/4. 1/4 times 9/16, so it's 9/64. All right. Flip the signs. Times 64. So you got a 6 minus 16r squared minus 12r and minus 9. Okay, let's try again. Synthetic division, let's go. $32 here. 24. 12. 9. Finally. So here we have a factorization. This means we have a factorization of r minus 3/4 times 64r squared plus 32r plus 12 equals 0. Okay. And the quadratic root, 128 minus 32 plus or minus square root of b squared minus 46. Let me just use that. 32 squared minus 4 times 64 times 12. Okay. And that's what? So this is 1024, right? 1024 times 2. 1024 is what? 1024 is, I believe it's 2 to the 6, no? 2 raised to the 6th power. No, not enough. 2 raised to the 10, I think. 2 raised to the 10th power. Yeah, that's it. So you should get a so this is 2 to the 11th. the 2 to the 5th, which is 32. And there's an I at the end. Minus 32, 32 cancels. So this still does not answer another question. My goodness, this is brutal. My goodness, this is brutal. Because where's the cosine of 1 over root 3 comes from? Because this complex root here solves one issue, solves this issue. But where does this come from, huh? Where does this thing come? Because this would correspond to a different complex root. We have this part. We have this root already. We have the 3/4. We have the 3/4. Where does this come from, huh? I don't get this term. We have 3 terms. 4 over 3, this is done. This is a mode of the... You sure about that? Nova? We have this root here. We have this root here because, right, I'm trying to say is, Bn satisfies what? Bn satisfies a third order difference equation. So Bn should have this form. Bn equals a r1 to the n plus b times r2 to the n and plus c r3 to the n. So r1 is rational, is this one. What I'm trying to say is there's no extra root anymore. This just corresponds to a different root. Because what does this look like? The cosine of n minus 1 theta, this comes from what? This comes from e to the I theta, I n theta. This comes from e to the I n theta. Why is there? Because this course, I mean, the idea is here you would have, if this is equal to cosine of n theta plus I sine n theta, Euler's formula. Euler's formula. So in that case, you would have something like that. You would have a real part, right? That's r. That's the real part of r, and something that has to do with 1 over root 3 I. I don't know, man. This is so confusing. I don't know, man. Where does this come from, huh? Where does this come from? I have no clue. Huh. So going back to, let's AI, keep AI this. So going back to the difference equation for Bn, use the initial condition. Use the initial conditions. B1 equals B2 equals 1 and B3 equals 1 minus P cubed, with P equals, and with P equals 3/4. Solve Bn. Yeah, this is the root. Hang on. I made a mistake here. I made another mistake. I can't really do high school algebra. Apparently that's the problem. I, for the love of God, cannot do high school algebra, it seems. If I multiply 4 here, you got 6. Compare this with the AI solution. This one. Can I at least scroll? Thank you very much. Easy. I know it should be easy. I'm a fucking idiot. Sorry about that. Here, this multiply by 4. For some reason, I'm not getting this one correctly. If I divide that by 64 is 4 times. This is not 4 times. No. Something is wrong here. Something is terribly wrong. I cannot do synthetic division. 64 at the bottom. And then you got 48. Not 32? Is there something wrong here? 64 minus 16 minus 12 minus 9. This factoring, I'm not getting it right. I'm not getting this factoring right. I'm getting this factoring. So I'm trying to divide this by 3/4. 32. This is so painful. This feels correct, no? This is not the same as this one. If we multiply by 4, you get 4r minus 3. That's 16r squared plus 8r plus 3, not 12r. All right, ChatGPT, expand 4r minus 3, 16r squared plus 8r plus 3. Here you made a mistake, huh? Because this is not right. But you wrote this. Yeah, so this is correct. Yeah, redo. Yeah, that's the root. I see. So the root is indeed, you see, this is the root, and it has the correct cosine value. It has the correct cosine value. So say this is minus 1, This is plus the square root of I. You can't convert this into, because the hypotenuse is root 3, right? So you can't connect this to an angle with cosine of 1 over square root of 3. You can't do that. So I think essentially this is a rather weird way to write the solution, because you either just reduce everything to sines and cosines, so everything is real, or you keep the complex notation, But you would never leave those two simultaneously. Okay? This is something you would never do. Because you either reduce everything to sine and cosine, like here. And you either leave everything to the complex coefficient. The distance you are factoring, maybe. This is correct. This is correct. I did it correctly. Thank goodness I still have my little bit of a sanity left. This is correct, huh? This is correct. This is correct. So basically, what I'm trying to say is just that the final answer being left here is rather awkward, because you would either convert the complex root into sines and cosine, or you would leave the complex root, just like in the Fibonacci sequence formula, right? So I think it's time for us to stop bothering with this question. Yeah, it's the same. It's the same. It's just that I've got to say, okay, problem 3 is problem 3, part 2, including part 1, okay? Part 1, part 2, part 3, and part 4, part 5 and part 6 are very worth doing. So these are the good parts, and the rest are just drudgery. It's just algebraic drudgery. Okay, so yeah, and let's not try to dismiss this entire problem as stupid. Okay, no, these are the good parts, and they are very much worth doing, because the idea of conditioning is being highlighted here. And Eternal also brought up a great point, that the problem can be seen as a Markov chain problem. So I just want to briefly mention that. Okay. So why is that a Markov chain problem? So we're considering the latest 3 consecutive outcomes as a state. So you got 8 states in total. Let's write head, head, head. Head, head, tail. Okay. Perhaps like this: head, tail, head, head, tail, 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 head, tail, head, head. Yep. Tail, head, tail. And tail, tail, head, and tail, tail, tail. So these are the 8 states. And what are the transition dynamics? So head, head, head can only become head, head, tail, or head, head, head itself. Right? Because the next outcome is either tail or head. So the latest sequence becomes either head, head, tail, or head, head, head. Next up, if it's a head, 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 tail, I mean, you can either have head, tail, head, like this one, or head, tail, tail, like this one. Next up, if it is head, tail, head, it can be tail, head, head, like this one, or it can be tail, head, tail, like this one. Okay? If it's head, tail, tail, it can be tail, tail, head like this one, or tail, tail, tail like this one. If it's tail, head, head, it can be head, head, head like this one, or it can be tail, tail, head like this one. Okay. Tail, head, tail, head, tail can become tail. Sorry, head, tail, head. So going back, or it can be head, tail, tail. So that's this one here. So that's the okay. That's not it. Every arrow has a probability. Oh, actually, it's not 1/2 because of the asymmetry here. The p is not 1/2. But I guess it's easy to write down the probability. If it's head, then the next one's a head, then it's just p. If it's not, it's just 1 minus p. All right. I'm not going to be super positive by these. Okay, and so the last one just finishes up. I'm just going to finish up drawing the dynamics. Tail, tail, head. Tail, tail, head can become tail, head, tail, which is this one, or become tail, head, head, like this one. Tail, tail, tail can be tail, tail, head, which is this one, or tail, tail, tail itself. Okay, that's the transition dynamics of the Markov chain. I'm pretty sure you can organize the graph in a nicer way, so it avoids intersection. So you would end up having a 8x8 probability transition matrix, transition probability matrix, okay? Probability matrix. Okay, so now we define a big T. We define the big T to be the minimum. And by the way, X is the state, Xn is the state, which is one of the 8 states. The state of the Markov chain. T is the minimum of n greater or equal to 3. N greater or equal to 3 such that xn equals head, head, head. So this is the minimum amount of time. This is like a first hitting time. So in stochastic process, this is called a first hitting time. The first time that this process reaches a particular state. Right? And what we want is the distribution of t. So we want is Bn, right? Bn is the probability of not reaching head, 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 no head, head, head in n steps. Right? No head, head in n steps, which means t is greater than n. So that's equivalent of finding the tail probability of, or the distribution of t. This is equivalent of finding the distribution of t. Okay, there's standard theory about finding the first passage time. By the way, this is called a first passage time. There's standard theory in Markov chain to find out the first passage time. Okay, which I cannot at the moment recall the formula. I'll have to look up in the literature, but that's the formulation. I think that's also worth mentioning. Okay, so we've streamed for over 4 hours today, which is, I think, kind of enough. Okay, so thank you very much, everyone, for joining the stream. Thank you, Vizzy, for submitting these problems. They are lots of fun, and certain parts are very interesting, I would say. And we managed to walk through, I would say, 2 important techniques in probability. One is you use the joint formula, The joint formula is pretty nice. And another one is conditioning. These are recurring techniques in probability theory used throughout, right? Especially if you're, let's say, if you're doing mathematical statistics, right? The first formula is perhaps more common. If you're doing stochastic processes, conditioning is more common. Okay, bro, meet you later with Stat Inference Live. Sure, go ahead. Yeah, we will do a Stat Inference stream next week, perhaps. I can't promise weekday streams, okay? But yeah, we can certainly do a Stat Inference stream. Start from the beginning. The first problem we can also solve by transforming variables with Jacobian. Yes, actually, you're absolutely right. You are absolutely right. So what Nova is saying is that, because I mean the question asks for the CDF, right? I mean it asks for a density too. So in principle you can use the Jacobian method. So basically you define another variable, say t. You can say t equals x. You can just say t equals x. Nova, is that what you had in mind? You can just say t equals x and then use the Jacobian method to get the joint distribution between of s and the other variable, okay, s and t. It has to be two variables because the Jacobian needs to be a one-to-one transformation. You can't just say it's 2-to-1, and that's never going to be 1-to-1. So you can define an arbitrary auxiliary variable, say t. You can say t equals x, t equals y, doesn't matter, as long as things are easy to calculate. And then calculate the Jacobian to get the new joint density, and then integrate over the auxiliary variable. This way you get the density that you actually care about, right? Yeah, very nice approach. Yeah, they integrate the marginal, exactly. Excellent approach. Thank you very much for suggesting it, because I kind of wanted to mention, actually, I kind of want to mention it, but I wanted to get to the second problem. Thanks a lot. All right, that's really it for tonight. Thank you very much for joining the stream. I'm glad I got the channel back, and there's going to be tons of new material coming to the channel. Complex analysis, stochastic calculus, mathematical statistics, and perhaps who knows what. All right. All right, that's it for today. Bye now.